top level management. Somebody was visiting, some government officials were visiting, and hence we'll just. So I am just coming in as a filler. Hope you will enjoy the lecture today. And this is on quantum hardware, because in the group, few of you were expecting that I will try to take something or somebody will speak something on hardware. In fact, different speakers have spoken on various aspects, but I thought I'll put up something for you, right? So let's take it forward, and hopefully you will enjoy this lecture. So quantum hardware, if you look at it, it starts from trying to understand the various aspects that we look at. So that is basically the central processing units, the cluster of processors, the grid of processors, which are heterogeneous. So initially, it all started with a single processor, and then the processing unit was what was there, and a single processor was there. Later, we went into putting multiple processors together or multiple systems together to create a cluster, maybe Intel processors together, AMD processors together, something like that. Slowly, we moved on to also combining multiple different vendors, their processors coming together. Maybe you can have Hitachi or AMD or Intel, all these things put together. You could create Motorola processors and then create a grid of processors and run them, right? Slowly, different companies also came in to give you the power using multi-core. Multi-core in the sense you will have multiple processors, in the sense multiple cores inside a single processor. So that also increased the power because after a certain speed that we look at the processing power, we see that it will generate a lot of heat, and hence they looked at different options. So one of the options that they looked at was trying to put multiple cores in a single chip. So from there, we move on to another kind of processor, which is called the graphical processing unit. Here is where we look at the graphical processing unit giving you more cores in a single chip. Now, you may ask a simple question: when 4 cores or 8 cores would generate a lot of heat, why not more cores generate less heat? So how can we have more cores? So the thought process is simple. We'll have more cores, but the power of each core will be less. So you can do more small number of jobs. Earlier, the processors, the Intel processors, AMD processors, they were doing a complex job, but less number of jobs, depending on the number of cores, 8 cores, 16 cores, 32 cores. So 32 jobs at a time. But when you look at a graphical processing unit, something like L40S today or H200 NVIDIA cards, they can do some 1,000 processes at the same time. So it is not concurrent, but parallel. So maybe you can look up what is the difference between concurrent and parallel. I don't want to go ahead. But here is where we'll try to move into what is called the quantum processing unit. So that's what is our interest today, where the chip is being created out of a variety of quantum materials. So the understanding we have done. And when we study the course QT-08, which will be on quantum materials, we will understand what are the materials that are used in creating a chip. Here also, if time permits, I will share some thoughts. But of course, otherwise, the content is there. You can read it. I will share it with you. You can read it later. So looking at this diagram, I think Mr. Sridhar shared in the first QT-01 at that time this picture. This is what is representative of a quantum computer, what it can do. So here is this is from Thailand or somewhere, and here is an image which talks about multiple hands and multiple brains. So you can look at this this person, if exists, right? He will be able to see all directions. So there is no way you can backstab him. You can't attack him because he is seeing all sides. So there is no way he has a threat. And then he is not only having one hand or two hands to fight with, he has multiple hands. So, and then multiple jobs can be done, multiple actions can be taken, multiple equipment can be used. So that is what is the thing. So if you have something like this, we can look at, you can do a lot of jobs because there's a humongous amount of power. So this actually talks about, brings us to the idea of non-deterministic finite automata, which actually talks about, I am at the same place and I see a particular symbol and I can go to multiple states. Actually, in a classical computer, it is like a deterministic finite automata where you see a input symbol and you move from one, you transition from one state to another state. So you cannot go to multiple states at the same time. It is like you get into one train, you will go to one destination. You cannot go to multiple destinations. But non-determinism allows it. You are in the same plane, and some people can say, I'm going to Calcutta, I'm going to Bangalore, I'm going to Jaipur. People cannot say like that, right? So the plane will go to one destination only. That is determinism. But non-determinism, just imagine if there is a flight which can take you to five to seven destinations at the same time. You get in the flight, you are still at five different destinations. So that is the power which we are talking about quantum. And how it is facilitated is what we are going to look at. But anyway, let us look at some interesting things that we see. What happened in the last 1 year? Actually, we look at the roadmap for quantum, it will be another 3-4 years. 2029 is what we see because people are talking about errors, people are talking about faults, people are talking about coherence, people are talking about noise. So all these things, when they are completely achieved, when we have the quantum advantage, we're looking at 2029, maybe another few years, maybe let us say. So that's when we'll have a fully functional quantum processor, which we can depend on all kinds of calculations. So that's where we look at. So that's where we have this November 13th, 2024, where the IBM Heron R2 chip came into picture. The latest version is what it is. December 9th is Google Willow. In fact, this was when we were actually planning the quantum series, where the quantum syllabus was published, right? Somewhere in December, the QT syllabus was published by as a minor curriculum by AICT and NQM, right? And then we have February 19th, where a prototype was released by Microsoft Majorana. Majorana is a different kind of material is used here, so we'll discuss that. Topological qubits, right? So that's the first topological quantum computer. It's still a prototype. They demonstrated a very small qubit, I think 8 qubit processor, but then they're going to build. And once it is going to work, topological qubits, they are ready to build something like 1 million qubits. So 1 million qubits means 2 to the power of 1 million states. So that is something that is going to be a challenge, right? But then you have Ocelot also coming up, which is also a prototype building by Amazon AWS. China built its own frequency, which is 3.0 something in March. And then I was trying to look at if there are any updates, not many updates, but a recent update was by Continuum. Continuum is a company, and Helios is the brand, or Helios is the chip that we can look at. Very recent, November, this month, right? Today we are at November 30th, 29th, and November 5th was when this chip was released, right? So you can follow, and then of course you can visit ChatGPT or what is that? Another large language model which will help you, right? Persistence or something, right? So these are chips. So you can look at this is how a quantum processor internally will be, right? There will be for a superconducting processor. So you'll have the superconducting qubits. There will be a tunable coupler. There will be a readout resonator. Readout is where you are measuring, where the quantum bits will get converted into what are called the classical bits, right? There will be some control lines and there will be a Josephson junction. So this is a superconducting quantum processor internal structure, how it looks like, right? So then we have these some of the brands which are there. Heron 2 is the fastest what do you say quantum computer at scale today, right? Heron 2, and we are fortunate that Amaravati Quantum Valley AQV will have the IBM Heron R2, which will be delivered. I think in January, another 2 months from now, we may have this processor available as a quantum computer in the Amaravati Quantum Valley. And this can be remotely accessed by many people across the state, different universities, different companies. They all can use the power of this IBM Heron 2. So this is the thing. And then if you look at the brief description of what it is, there are 156 physical qubits. Mostly you know that, but then it uses the superconducting qubits called transpon qubits. They behave like artificial atoms. So each transpon is essentially a non-linear resonator made of Josephson junction. Right now, I may not have that much of time to discuss these, but we will come to these kind of hardware when we talk about the materials, quantum materials. At that time, you'll understand some of these concepts, right? So I will leave it to you to read and understand what is Josephson junction, right? So they are cooled to absolute zero. It is called 15 millikelvin, and that is where you need dilution refrigerators. I'll show you the architecture of how a dilution refrigerator looks like, right? Then Heron introduces tunable couplers. We have just seen the tunable couplers in the architecture between the qubits. So each qubit is connected by a dedicated coupler element. And then each qubits connect to at most 3 neighbors using a heavy hex lattice topology within the IBM Heron R2, right? So this is the internal architecture of IBM Heron R2. Uh, Google Willow, it came with the quantum advantage. It talks about 100 plus qubits, but then it talks about error, low error rate. So that is the advantage that we look at. And it talks about 105 qubit superconducting transform processor. So it is one way less powerful than the IBM Heron 2 because it is 165 bit and there's only 105 bit. But the basic advantage that you look at is there is an exponential, what do you say, error reduction as scale increases, right? It marks a milestone known as below threshold, right? It's a below threshold. It is first achieved by a superconducting system. So when they use the random circuit sampling benchmark under 5 minutes, a task which will take about septillion, 10 septillions. So that is 10 power 7 years, right? So many years that you can look at. That was done within less than 5 minutes. So this was tested, and that is where you can see that the error reduction was below threshold, right? So lowest threshold was achieved on the error reduction. So that is where the Google Willow is popular, though it is not 165 qubits, only 105 qubit. Then Majorana is what we look at. Majorana 1, Majorana 2 also is there. But then here we look at topological qubits, which are there for stability. So it is not superconducting, it is topological. So it is the first quantum processor which is based on topological core architecture. And they leverage what are called topoconductors. Like semiconductors, you have topoconductors, a novel class of materials. So it is only an 8-bit quantum processor, but it functions as a proof of concept and it showcases the feasibility of topological qubits. So it is not a fully built processor or a readily commercially available processor. It is being tested and then it is being done. But then what is the advantage here again as you look at? It is a transformative leap towards scalable fault tolerant quantum because topological qubits will not need that much of a low temperature. That much of decoherence is not required. So they are very much coherent. So you don't have to create what do you say, the coherent environment, right? So decoherence is very less. That's what I mean to say. So basically what they're looking at is if this prototype works, we just scale it. It's very easy to scale it. Once you build a model, you can scale it. So they say we'll scale it up to 1 million qubits in a small chip footprint. So that's what we can look at. Then as Ocelot is what AWS talks about. AWS talks about bracket also. Maybe you may have heard about AWS bracket. Bracket uses IBM computers only, but then bracket provides the quantum power as a cloud offering. That is what AWS bracket is. But Ocelot is the processor, and they use what is called cat qubits. What are cat qubits? Cat qubits, it's also a prototype. It's not a really functioning thing. So it is based on superconducting circuits called bosonics. You must have heard of fermions and bosons. So here is where bosonic error correction using cat qubits. Again, we'll study more about bosons and fermions later also. I think QT-02, you were introduced to these fermions and bosons, or in this course itself. So here we have what are called cat qubits, right? So cat qubits basically is a design that inherently suppresses specific error types. Just like you had very less error rate in Majorana or in Google Willow, here also Ocelot also is talking. But Ocelot is also not a fully implemented processor which will actually use what do you say, this thing. So that's something that we can look at, right? So it demonstrates bit flip coherence approaching 1 second and phase flip coherence, which is even approaching 20 microseconds. That is a very less time that it takes for demonstrating a coherence, right? It reduces quantum error correction by 90%. You don't have to correct the errors because the errors are very less. So if less number of errors, the time taken is less, and of course the time is reduced by 90%. So that's the power of Ocelot. But of course, it is fully not realizable. But side by side, we have this powerful processor which has come out, which is called Zushon-Z. This is a Chinese processor and a very powerful quantum processing unit called Zushon-Z. It is almost competing with IBM Heron 2, but it is still to move up to because there's a different architectural power there. So though the chips, the qubit may be less, but the power will be more. So that's what we can understand. But it still uses superconducting transform qubits, 105 in number. They are arranged in a 15/7 rectangular lattice. But the beauty is there are more number of tunable couplers. There are 182 tunable couplers where two-bit interactions can very easily facilitated and there will be no crosstalk. And it uses a flip chip 3D packaging mechanism where two sapphire-based chips are bonded via indium pumps. So you have two layers of one above the other. There are two qubit circuits separated by a indium pumps, and then they are packaged into a single chip. So that's what we can look at. So there, it was a random circuit sampling task, which we were previously also discussed. It used 83 qubits over 32 cycles, producing 1 million samples, right, in mere 100 seconds. We talked about previous benchmark, which took about less than 5 minutes. Here we're talking about few 100 seconds. So maybe 120 or maybe 200 seconds, like 3 minutes, which approximately would have taken on a classical computer 6.4 billion years. So you can understand the quantum advantage that is coming up, and this is physically realized. Very recent, the latest that you can look at is Quantinuum Helios, which is by a company called Quantinuum. This is what is used in the processor called RIKEN, right? RIKEN uses this processor. Here is where you can have it. Basically uses a quantum charge coupled device architecture. It uses 98 barium ions as physical qubits. So this is the trapped ion mechanism. Trapped ion qubits is what you can look at, right? It basically spatially separate regions for storing and performing logic operations on qubits, which enables all-to-all connectivity, right? The strength is basically high fidelity. When you talk about high fidelity, it means low error rates. High fidelity is a metric, okay, which talks about reliable quantum computation, and the fidelity is 99.9%. So there is an error of 0.01%, right? Something like that, right? So the logical qubits are about 94 quantum error detected logical qubits are taken. And it also develops a programming language called Guppy, which is a Python-based programming language. And it has the software stack. Maybe yesterday, as Lakshya was talking from QPI AI, he was also talking about a stack, right? The stack involves a programming language to interact with the processor. Right? So a programming language specifically designed so that it understands the quantum hardware, right? Earlier were the days when people had the hardware-based things. When later operating system came in, the hardware is controlled by the OS, and the actually compiler started building based on the OS itself. So OS-based compilers for a Windows, for a Linux, different versions, the compilers will be different. But hardware can be anything. So we have made it more platform independent in that context. But here is where when you're using quantum processors, you will need some software stacks which understand the quantum. The basic idea is to optimize it. Otherwise, you will use classical stuff over a quantum processor. The full strength of a quantum processor may not be available because you are still talking to it in classical terms, whereas it is a quantum processor. So that's something. And then we have been hearing about CUDA-Q. Mr. Anand Raman also demonstrated this time about how to run parallel processors. In the last course also we had how we can integrate or hybrid GPU and CPU and QPU combinations that we can look at. So that's something which we can look at, right? So these are some diagrams. I'll just quickly skip through them and we'll move to the next part. That is how an IBM quantum computer looks like, right? So there are different processors which have been used, and 133 qubit Heron processor, which is the release one was 133 qubits. And of course, you had the cloud platform, which is there. You can access some of these things. So that's these are the processors which are given access, which we are given access to, where we can try to run our codes using Qiskit, right? So these are the things. And then it has a fully fault tolerant quantum computing, FT QC is what they are trying to look at, right? I'm just quickly introducing few quantum computers which have been created. D-Wave is another quantum computer. The internal architecture is what we are able to see, the whole thing that is there with all the wires and all. So D-Wave is another quantum computer, and then it's commercially available. It's the world's first commercial quantum computing supplier. Okay, where people were selling that, and then of course you have a quantum access, a cloud access also you can have. It also uses hybrid solver integration, where you can run a variety of things, and there's energy efficiency. It doesn't take much electricity. Then you have the Google Willow quantum chip, and then they have their own quantum processor, and they have achieved better this thing. So the strength is the reduced error rates, faster performance, and increased qubit scalability. Rigetti is another company. Please remember all these things. So if you are looking for careers or jobs, these are the companies which will employ, provided you have good understanding of the hardware, good understanding of the programming or simulators, or good understanding of quantum mechanics and mathematics like linear algebra and others. So this is what actually what we are looking at, right? So please remember these names of the companies. Most of them may have India-based opportunities as well. Of course, they are all based in other countries. In India, we have only QPI, and we wanted to have QNew Labs. And there are other few companies, small companies, which are there. We'll try to bring them to talk with us so that we'll understand what India is able to do and what we should be doing, right? So here is Rigetti, which is basically a universal gate model quantum computer, which uses the tunable this thing. It is also a full stack quantum company, right? It has develops everything from quantum chips to the software that the programmers use to build algorithms. So everything is included in when you look at Rigetti quantum computer, right? So these are the, again, it's a superconducting qubits that we look at. It's a multi-chip architecture, a unique architecture designed for scalability, which may move towards thousands of bits slowly, right? The custom instruction language is there called Quill, just like we had Guppy or Guppy. Here you have Quill, the quantum instruction language, QIL. So it facilitates hybrid quantum classical computing, right? So you can run both the things. So people who have used CUDA, CUDA, which you use with NVIDIA, so you can integrate CUDA and C and run the codes on a CPU GPU combination. So in a similar sense, now you can use what do you say, the open source Python tools along with the quantum instruction language. So you can integrate CPU GPU combination, CPU QPU combinations. That is what people look at, right? And then these are designs are made in their in-house fabrication. They have a Fab 1 facility, so that's what we can look at as far as Rigetti. Then the next company is IonQ, is a quantum computing company. General purpose quantum computers are created. Here they use what is called trapped ion technology. We were discussing the last quantum processor also, which was based on trapped ion, which was the Helion by Quantinuum, right? So the other types of quantum computers are there, which are superconducting or photonic ones. But here you use individual atoms as its qubits. In the previous case, it was barium, right? So these charged atoms or ions are suspended in vacuum and manipulated with lasers to perform calculations. So here the requirement will be vacuum control is what is needed. In the superconducting, what you need is temperature control. So that's what we can look at, right? So they are qubits from nature. So they are taken from ytterbium or barium, right? So they make them highly stable. So there's an all-to-all connectivity. So when you look at in the previous, we talked about couplers, tunable couplers, where there are few-to-few connections. But here there is an all-to-all connectivity because of that. And there's a software configurable architecture. So you have this, so you can reconfigure the system with software. You don't need to make changes in the hardware. And then again here also, because it's trapped ion, you have high fidelity. We looked at Helion, which has high fidelity. IonQ also has high fidelity, and of course, Helion will have better than IonQ because it's a very recent one, right? So you can look at those processors. And then this is our own Indian TCS DRDO TIFR built a 6-qubit quantum computer, maybe the initial version that we can look at using superconducting technology, and which was done end-to-end testing was possible with the National Quantum Mission. TIFR focuses on qubit design and fabrication. DRDO gave the control system and hardware. TCS developed the front end or the cloud-based interface, and of course the software tools that are required for the processor. It's also a full stack computer, but it's only a 6-bit quantum computer. Yesterday we listened to QPI-AI, so QPI-AI. So it's a full stack quantum computer launched in April 2025, very recent as we look at. And then you have the superconducting qubits and your scalable control systems. Of course, AI enhanced quantum software, as yesterday I had asked, how do you integrate both these complex things? AI is also complex, quantum is also complex, but then they are trying to make it a hybrid quantum architecture, right? So basically, it's a 25 qubit superconducting computer and 128 NISQ noise scalable quantum computers. So 128 qubits and 100 logical qubits. They are looking at from 25, they're going to 100 by 2030. So another 3-4 years, we'll have a very powerful thing. And then there's an integrated HPC software where you add AI tools using QPI-AI Sense. It's a control interface, and then it optimizes using QPI-AI Opt, right? So it's a full stack system, advanced quantum processors, scalable control systems, optimized software, all these things that are there. So basically a deep science and deep tech innovation, which is actually helping QPI-AI. So that was the first part that I wanted to share with you. Now we look at the second part, that is what is actually involved, because we talked about what are quantum processors, right? Now let us go into a bigger version of what is a quantum computer. What are all the parts of a computer? We talked only about microprocessor. If you look at a classical computer or a desktop computer, we looked at what is a processor, that's all till now. Now we look at all the components. What is a motherboard? What is all those things? How the signals are sent? What is there in the motherboard? What is the RAM? All those things we look at in these. So these are the items that we look at. Just give me a minute. So these are the quantum components of a quantum computer. Right, many times I also was looking at a lot of diagrams and thinking, okay, this is a quantum computer. But what does it all comprise of, right? So that's what we are trying to look at. So we have the quantum processing unit, which we have discussed, but we'll see where it is placed. We look at the cryogenic system, which is the dilution refrigerator, which we look at. Then the control electronics, the wiring and control lines. There's a readout system, and of course, a quantum software stack. Classical computer backend is a normal classical computer, a laptop or a desktop, mobile phone also. You can just connect and then you can, it's a device which displays the power of quantum, right? You can connect to a quantum computer in any of the device. So that's what is a classical computer background. So we don't have to really look at that, but the remaining aspects is what we try to look at. So this is the broad diagram. Maybe you can take some time to look at that. So the inside part, the U-shaped is what is the dilution refrigerator, but it's not U-shaped. It can be like a rectangular box, which you'll see shortly. Yesterday he showed also. I showed also sometime earlier. We can look at that. So this is how a diagram looks like, right? So there are quantum control wires which are coming from top into the top layer, right? And then you have multiple layers. As you look at, there is a what do you say, a V kind of a shape. You have the a broader ring on the top, a smaller ring, and then a still smaller ring, and still smaller ring. So the diagram goes like this, right? So that is what exactly here. So at each level there is a temperature variation. Okay, outside is room temperature, right? Outside that U is a room temperature. So all the readout system, the quantum software stack, the control electronics, the classical computer backend which you are accessing the cloud, they are all at room temperature. Only the temperature is maintained within that small thing, and it goes down actually from the top. Top is hot and then you go down, cool, and towards the last, you have the very cool thing. So maybe if you look at on the left-hand side, you have classical computer backend, okay, classical computer backend, which is normal computer, right? Then the control electronics. So you talk the first level that we talk, like how you have lines on a motherboard of a processor of a computer. In the motherboard is there are a lot of control lines. So that's the control electronics that we talk about, right? And and then below that we see that quantum processing unit. Quantum processing unit is actually pointing to a small chip here. So the chip is shown here. This is the chip. Hopefully you are able to see the arrow. So that is the chip, right? So the chip will be at the lowest level. This is not the actual diagram. This is a conceptual diagram. So we're trying to understand the concepts, right? So that's where it is. The chip will not be this much size. That chip will be very small in that sense that compared to that, here if you look at the chip may be only of the size of the wire, right? A very small chip, right? Or it will be placed in a device in a even cooler temperature, and hence you can look at that. Then all those control wires are there. Apart from that, there is a readout system. Readout system is actually what is measurement, right? We looked at that 6 fundamental thoughts of quantum computer. Maybe if you remember, right? Superposition, entanglement, interference, right? Then we talked about decoherence, right? Or noise, right? So that was the other thing. And then we looked at measurement, right? So, and then one more thing is decoherence, and the other one was noise, right? Noise and decoherence, two different things. And lastly, we have what is called measurement. So measurement actually is what converts the quantum bits to classical. Quantum information becomes classical information, which you'll be able to read and use. So, and then a quantum software stack, which actually converts, reads that material. So if you want to talk to the quantum computer, you talk to the quantum stack. So classical computer will have a quantum stack. Quantum stack will talk to this quantum, this thing, the control electronics and the readout system, and then the actual computation is done on the processor. The pulses are sent using the control electronics. The inputs are sent, and the computation is done on the quantum processor, right? So hopefully you understand that. This is a recent diagram which I requested from IBM. So this is used with permission. So this is only for the discussion purpose. So please understand that this is recently I took it from Dr. L. Venkat Subramaniam. So this is the central part that we look at. So this is the cryogenic chamber, right? So this is the cryogenic chamber. This is the cross section. What we are seeing here is a cut part. If you cut out, this is what actually inside what you see. And at the bottom of the bottom of that is where you look at. This is where the quantum processor is placed. The lowest part is where the quantum processor is placed. And the temperatures, as you look at, the temperature will be high here, little low here, little low here, little low here, and then this will be the lowest at the quantum processor, right? So there will be cryogenic amplifiers. There will be some microwave signal isolators. Then there is coaxial cabling. There is thermalization and cryogenic stability, which the wires are coming from top. Then left side, you see all the microwave sources, the analog microwave components and digital signal digitization, which is basically sending inputs. Now, whenever you are talking through a normal processor and trying to communicate with the quantum processor, the information flows through these microwave sources where the inputs are given, right? So the FPGA-based microwave pulse shaping control units are there. All these things will talk. So when you look at, it will be a big chamber-like thing, and then you can see that. So there is these things. So please remember these. What do you say? You have these, holding things, which are actually trying to place the what do you say? The dilution refrigerator on top of that, right? It's a casing which is actually keeping the temperature very low inside, right? So that's what we can try to understand. So yeah, so quantum processing unit is the heart of the quantum computer. It hosts the qubits and implements the quantum gates. So we also discussed quantum gates yesterday. Also, there were some demonstration of various gates being connected, and also we had some lectures on the quantum gates and also implementation of quantum gates Mr. Dr. Jaykumar mentioned that, right? So you have host qubits which implement the quantum gates, right? It requires extreme isolation and low noise. So that's the quantum processing unit's requirement. And then there are multiple ways of having this quantum processing unit: superconducting, trapped ion, neural atom, and photonic and spin, right? So these are the items that you can look at, right? So the quantum processing unit, so there is the classical electronics which gives the inputs, and then you have the cryogenic chamber, and then you have the various plates. The plates are placed at different levels. The plates are connected through some gold wires, which are made of that material, and then at the bottom is what you have the quantum processor, right? So this whole thing is a quantum computer, and the quantum processing unit is actually here, and this is what is called the cryogenic chamber, right? So the entire cryogenic chamber is this part. The cryogenic chamber is connected to the classical electronics through some cables, wires and cables. So this is the quantum processing units. So when you look at superconducting qubits, which are by companies like IBM, Google, and Rigetti, so they use superconducting qubit systems. It is inside the cryostat dilution refrigerator, inside that box. At the lowest portion is where you have the quantum chip, right? So this whole thing is a quantum computer, and this is a quantum processing unit. So within the dilution refrigerator, the quantum processor chip is placed. So where is the location? Location is inside the cryostat dilution refrigerator. The quantum processor chip is mounted at the bottom state of the dilution refrigerator. We look at the dilution refrigerator shortly, so we'll see the temperature difference. So the lowest level is 10 to 15 millikelvin MK. So very, very chill, minus 270 degrees centigrade. So that's what is what we look at, right? It is the bottommost, deep inside is the bottommost part of the cryogenic stack at the cold plate, which is approximately 10 millikelvin. Inside a quantum vacuum chamber surrounded by multiple thermal shields. So you have this thermal shield. That box is a thermal shield, the grip that I talked about. So that is the thermal shield. Inside that you have a temperature maintained at 10 millikelvin, right? So that is something that we can look at. In a trapped ion computer, so these are different types of computers. Maybe sometime again, when I have a time, I'll share that, because we are almost towards the end of that. So I'll not be able to introduce all these things, but three things that we are looking at. One is the superconducting qubit systems. The second one is the trapped ion qubit systems, and then we look at the next one. So three aspects. So here is trapped ion qubits. We looked at IonQ, Honeywell, and Continuum. Continuum company also, Honeywell is the organization which is sponsoring, and then they are building the Japan-based quantum computer called RIKEN, RIKEN. You can look up RIKEN, right? So it's an ion trap chip placed inside a vacuum chamber. So there is a vacuum chamber. Inside the vacuum chamber, using lasers, you try to set the communication. In the case of superconducting qubits, you send through the superconducting elements that you can look at. But here is where you looked at the trapped ions, which are controlled using lasers. There you have a small chip. So it's a small ion trap chip placed inside the vacuum chamber. The laser and electromagnetic fields control the trapped ions. So it is inside the ultra high vacuum chamber, and this is typically at room temperature, but it is isolated, okay, completely in a vacuum, right? But it's at room temperature. You don't need a cryogenic system for trapped ion computers. So trapped ion computers are from IonQ, Honeywell, and Quantinuum, right? When we look at the last one, that is, there are many, but I'm looking at three things that we are discussing. The photonic quantum computers, it's an integrated photonic chip inside an optical cryostat. Here also temperature is to be maintained. So you maintain a cryogenic module inside an optical table enclosure. Here you have companies called Xanadu and PSI Quantum. They make this photonic quantum computer. Xanadu was the company which came out with the penny lane. So the penny lane architecture will work on quantum computers. So that's what we can try to understand, right? So most of the electronics are outside the quantum processing units, right? So all the classical electronics, that is control electronics, microwaves, FPGA boards, they are all outside. We have seen that diagram. They are outside the cryostat. The cryostat is only to maintain coherence and noise control and the temperature control, so that at low temperatures you have a very strong advantage that you look at, right? Separation is necessary because electrons generate heat and cannot survive the cryogenic environment. So this is how a cryogenic system looks like, or the dilution refrigerator looks like, right? So the middle one is what is a Riken. The first one is Riken, I think. Yeah, Fujitsu also, and then the Riken computing systems, and the third one is QPI AI. So Fujitsu is another company, but Riken quantum computer uses what has been created by Fujitsu, right? So these are the dilution refrigerator. And basically, you maintain a very low temperature. As I talked about, at various levels, the temperature will reduce. This is what happens. On top is the classical control units, and you have the room temperature. They are all at the room temperature. That's why they are outside. That's why we said electronics are outside the cryogenic chamber, right? So the wiring goes inside, and there are multiple plates, right? At every plate, the temperature is dipping down. Initially, it is at 4 Kelvin, then it comes to 50 millikelvin, then it comes to 10 millikelvin, and then it goes even around 10 millikelvin is where the quantum processor will be available. But the outside temperature will be at the room temperature, right? So within the quantum temperature is where within the cryogenic state, right? The 4K state, 800 millikelvin, 100 millikelvin, 10 to 20 millikelvin is what we can look at. So basically, why do we need this dilution refrigerator? Here, electrical resistance is zero. Thermal noise is minimal. There will be still some noise, but it will be very minimal. And then we look at electrical resistance, it will be zero, because at that temperature, the electrical won't work. So that's what we are talking about, right? And qubit coherence times are maximized. So at room temperature, thermal photons would instantly destroy quantum information by cooling to millikelvin. Qubits stay their quantum ground state, and that's where the quantums will stay because they are the quantum ground state. So the difference, there's a difference in the requirements of cryogenic systems, as I already mentioned. Trapped ion qubits are not theoretically refrigerated, though they also try to be kept in a refrigerator because it is actually it doesn't need that low temperature, right? It can be operated at room temperature. What is required is vacuum, so you don't need a dilution refrigerator. In photon-based quantum computers, the optical components traversed by the photons, that are mirrors, prisms, interferometers. We studied some of those optics concepts. So they are not refrigerator. But the photon sources and the photodetectors are temperatures between 1 Kelvin and 10 Kelvin. And hence, they are refrigerated, right? So not millikelvins, please note. But then when the cold atoms that are there, they are suspended in vacuum using a Doppler, right? And then when you look at for different qubits, the silicon components that are used in photon-based electronic cooling techniques, right? So the cooling capacity is very low, very, very localized. It requires pre-cooling the system to at least 244 millikelvin. Therefore, necessary to still operate at helium-3 and 4 dilution cryostat. So the material used to keep the temperature low is helium-3 and helium-4, right? So these chemical component is used to maintain that temperature, right? Lastly, we have the superconducting qubits, which require a temperature of about 15 millikelvin, approximately 10 to 20 millikelvin. So cryogen is basically the key quantum enabling technology, particularly for solid state qubits, which work at room temperatures. So that's what we can look at. Not room temperature, work at temperatures between 15 millikelvin and 1 Kelvin. The cryogenic systems, basically, it uses the dilution refrigeration, which is based on association of two helium isotopes, helium-4 and helium-3, which have different and complementary physical properties. You mix them, they have respectively different boiling temperature, 4.2 Kelvin and 3.2 Kelvin. Helium-4 is superfluid, right? Helium-3 is superfluid at much lower temperature, right? The cryostat exploits the combination of these three phases, a gaseous helium-3 phase and two liquid phases, one with 3 helium and other with mixture of 3 helium and 4 helium, with evaporation of 3 helium in a mixed chamber, right? So how this is maintained and how these helium-3 and helium-4 are used and how they are managed, you can, of course, look into any this thing, right? So these are what are the quantum electronics. So a lot of microwave pulses, they are all sent using the quantum control electronics, right? Maybe I'll try to put in a more clearer picture this was also shared by one of the resource person I picked up from there, right? Generate precise pulses to manipulate the qubits. Those are the control electronics. Like how you have a keyboard, when you type on a keyboard, there are electrical pulses which are sent to the computer. So these are the pulses which control the data which is handled by the microprocessor and what is displayed on the screen, right? It goes to the processor, from the processor it comes out to the display screen. Same is the case when I want to talk to the quantum processor. I have to send the pulses which are basically sent through the control electronics, right? So there are digital analog converters, analog to digital converters, microwave sources. Many of those things are there, and they are all available for room temperature classical processors. They help in creating that, right? So then emerging cryo CMOS electrons also are there, which are there within the bridge. And there are hundreds of coaxial cables and DC lines which are there, which are wiring and control lines. Thermal anchoring is done at each cryostat stage, and then they are connected to room temperature electronics at QPU. There are filters and attenuators and amplifiers which are integrated to create that architecture, right? The most important thing is the readout system. Readout system is where the quantum bits are getting converted to, or they are measured and they become what are called classical bits. Right. So the components are readout resonators. They use Josephson parametric amplifier (JPA) or Josephson's traveling wave parametric amplifier (JTPA). Right. And then you have microwave filters. It basically converts the quantum states to classical bits. And then, of course, the classical computer backend, which can be basically any normal computer which runs as a backend, right? It can run hybrid algorithms like variation quantum electronics and QA, and QAOA, and controls calibration feedback loops. It's a high-speed link to quantum processing units. And lastly, you have the quantum stack. The quantum stack is different frameworks that we use: Qiskit, CIR, Q hash, bracket, and Perylane. So they are all the quantum stack to interface with the quantum processor. So that's what we can look at. And I think I'm also coming towards the close of my talk. So these are the hardware implementations that we talked about. And I think one of the resource person, I think this slide is from Mr. C.V. Sridhar, who talked in QT-01. So these are various quantum hardware implementations. The material is there of all these things, but I will leave it here because we are coming to the end of the session. So if there are any doubts, I'll be very happy to look at. If there are any queries, I'll try to answer that. We will stop here. These are the hardware implementation, and the slides continue with all these details of various things. So I will share the slides for your convenience. They are picked up from various types of material which are taken, and superconducting, trapped ions, photonics we discussed, right? Quantum topological also we discussed. Only quantum dots is what is missing. So if there's anything that you can look at, yeah. So if there are any questions, I would like to answer, and we'll give you these slides we'll share so that you can try to look at all these details. Yeah, if you have any questions, I'll be happy to answer. As of now, as we look at Heron is what is available. Condor and other processors of IBM are also available. So, and then Google uses its own Willow, and AWS offers bracket, but the background of the bracket is an IBM processor. So, by and large, quantum computer price of a quantum computer is done in a few crores. The 25-bit quantum computer, which was created by QPIAI, costed them 25 crores. And I was also trying to discuss with them. So roughly a 8-bit quantum computer, quantum processor and the quantum computer, the whole equipment will be roughly 8 to 10 crores. That's what I gather. So if you want to set up set up a quantum computer, it will be about something like 10 crores. But then, yes, what you can look at is the IBM Heron is available. So as we look at that part, you can try to understand how it can take it. The BTech students, what is the syllabus can be included? Yeah, you can just introduce these hardware implementations. You can tell them, you can describe that whole quantum computer, the various components of the quantum computer, what it all involves. And actually, you can make them understand how how a classical computer works, how we give the von Neumann architecture and explain the thing. Something like that, we have to give the quantum architecture. Is machine learning is brought in along with quantum, whether there is any difference that occurs for the real and world problem sharing with the, yeah, see, yeah, as I explained, CPU was initially used for machine learning. When you looked at deep learning, you use what is called GPUs. Okay, so the CNNs and all those things, when you want to run them, the TensorFlow libraries, they run on maybe a Google Colab, you don't understand, but the below the Colab, internal architecture is actually GPUs, graphical processing units, where a lot of parallel processing is required, right? Now, in a similar sense, a lot of parallel processing, I want to increase even further. So maybe it takes 3-4 hours for a very powerful problem to get solved, even on powerful quantum processing units. Maybe I want to do it in few minutes. Then I will need the quantum power. So that's where if you are scaling up, the data sets are becoming bigger and bigger, and they may take few days to analyze. And if you use a quantum processor, if you write quantum algorithms, quantum machine learning algorithms, it will reduce to few days, few hours. So that's what I would say. Is there any work at present in which NISQ can be handled at room temperature? Room temperature is what I talked about, trapped ions, right? So, but then the way to maintain that is using the vacuum, and manipulation is using laser. Obviously, the errors will be more. Errors will be less in superconducting, but the requirement is of this thing, that is the cryostat, right? A dilution refrigerator. Large amount of electricity is wasted at just refrigeration part and other. Yeah, so trapped ions is the alternate, but then the errors will be more. So reducing errors is the challenge, which even Majorana and other pros are also doing, right? We get to see so much on QSIT, but rarely get to hear Amazon Bracket SDK. Can you please throw some? Actually, yeah, not many have used the Bracket QD quantum development kit. That's what I fully agree. But Bracket is actually providing the access using Bracket. Bracket is a term. Of course, Bracket is also a framework that you can look at, but it is running on IBM. So the Bracket will be quite similar to Qiskit. So if you know Qiskit, Bracket will be easy to learn. So underneath the Bracket is, as of now, it is IBM, but then slowly, as you look at Ocelot will slowly replace. Something about quantum dots. Yeah, quantum dots was discussed earlier. So let me quickly take you to quantum dots. Yeah. So quantum dots, basically, they have charge or spin states, Ket0 and Ket1 as used as qubits. So basically, they use materials like silicon and gallium arsenide to create the quantum dot qubits. So basically, there are two different types of qubits. One is called spin-based qubits, and the other one is the charge-based quantum dots. So these are the two things, and there are hybrid architectures which you can combine both of them, right? So that's the kind of thing. A lot of work is going on in this area, so you can try to understand how these things are built. And you also have a single qubit system and a multi-qubit systems where single quantum dots confined to individual electrons for single qubit operations, but an array of coupled quantum dots are used for implementing two-qubit gates. So that's something. As beginners, beginners, please start with understanding the mathematics and the physics part of it. So that's the first step. Secondly, pick up any simulator, trying to understand how to run quantum codes, understand quantum gates, try to create quantum circuits, and then try to implement those things. Now we have, my time is up. We have Mr. Raja Singh Yadav from CDAC. So we will request him. He will run us through a quantum algorithm. So that's the first step. Please understand the simulator, then understand the tool or the language on which you can write. Python basically is there, and then you implement the whole thing using that part. So you can try to look at that. How can we sufficiently isolate a large-scale qubit system from its environment to prevent decoherence? So the basic idea is the dilution refrigerator that we're talking about for superconducting qubit systems, and the large-scale qubit systems presently available only in superconducting qubits, 165 qubits we looked at in Heron. They're going to go to 1,000 qubits, something like that in a couple of years. So that's what we look at. The basic idea is manufacturing of materials is not a problem, but keep maintaining them at the temperature will be the biggest challenge, right? So let me stop here. I'll take the questions after we finish the next lecture. So I will stop sharing, and I'll take your questions towards the end once we complete today's lecture. So at this time, I'm very happy to introduce Mr. Raja Singh Yadav. He is a developer in Q-inverse. Q-inverse was found and developed by CDAC Bangalore. So Mr. Raja Singh works with that. So I request Mr. Raja Singh Yadav to take us through one algorithm, which we will, of course, anyway study in quantum computation. Sir will take us through one algorithm, and then he will show the implementation of that, hands-on implementation of that on Q-inverse. In the last half part, he will explain the algorithm, because we don't know all the algorithms as of now. Though you have studied some VQA and some machine learning algorithms, some computer vision implementations you have seen, but I'll request. Sir, would you like to share your slides or something? Hello.
Yeah, I'm audible, right?
Yeah, yes, sir. Yes, you're audible.
Yeah, just a minute. Yeah, okay, I'll just share my screen.
Yes, yes.
Yeah, can someone confirm my screen is visible?
Yes, sir. Yes.
Yeah. So
You can.
yeah,
Yeah, you can take
I'll
it
just
over.
put it.
Yeah. Welcome to Mr. Raja Singh Yadav. Participants, please. We'll go through the entire algorithm on the Deuce algorithm. Yeah, or Grover's algorithm. Yeah.
So
Thank you.
should
Thank you
I
so much.
like yeah, so should I go for Dosh or Grovers? Like I can give
Whichever.
both.
Whichever. No problem. Sir. No problem.
No
Grover's is
problem.
fine, because they have heard of all these algorithms, so you
Okay.
can take them through the algorithm and then discuss the implementation.
And they are
Thank you.
very much comfortable in like basics of this quantum mechanics and linear algebra, how one
Yes.
state
Yes.
like we transfer from one state to another state, right?
Yes, sir.
Like
They are
state
aware
vector
of.
notations and all. All
Yes,
right.
sir. All
So
those. Yeah.
okay. So okay. So in this session, this 1 hour, I'll go through this quantum, one of the quantum algorithms called Grover's algorithm. And once this, I'll explain the theory behind it. Then I'll show on the Qnus platform how we can generally work on this part, like how we can implement this Grover's algorithm. And I'll also tell what are its drawback, like since Grover's algorithm or the quantum algorithm which we study is mostly in a probabilistic nature, and our team has developed a deterministic also, like, so I'll come to that later also. So in this overview, there's overview of this algorithm which we have. First, I'll talk about this problem statement, what exactly Grover's algorithm is, then how we can do the comparison with classical with the quantum part, and what is the solution of Grover's algorithm, how we can search the element, and in the end, I'll show you how I can or you can also implement onto our Qnus platform. So the target area is like structured and unstructured databases here. So when we talk about Grover search algorithm, it generally deals with the unstructured database. Means like all the elements which you're having into your Hilbert space, they are totally I mean they don't have any proper index where exactly it is located. Since all these elements are already in a superposition state, so you have to find it out the exact element is it there or not into that particular database. And how to do it, I'll commit later. Before that, this is one of the scientists called Love Grover actually. He generally developed this algorithm back in 1996 itself. So at a very early time, even in 90s itself, he has developed it. And this is like the second major algorithm proposed for the quantum computing. Before that, the Duchosh algorithm, it was already developed. So this was second quantum algorithm, like in quantum algorithm people came with, and it has actually shown a very good advantage also. It has shown that you can find a marked element, and at the same time you can get a quadratic speed up compared to the classical also, not exponential one, but a quadratic speed up for searching an element. For and to get exponential speed up, that's where Shor's algorithm came. So Shor's algorithm gave exponential speed up, whereas Grover's algorithm gave a quadratic speed up. So first I'll go through this problem statement, what exactly it is. So the problem statement is like, suppose just like you all are CSC students, right? So we have an array here from 0 to 7, correct? 0, 1, 2, 3. This is its index number. Along with it is having some number in that one. Like, and the idea is like I have to find a particular number called 66. So the question is like, at which index this 66 number or element is as of now at the current position. I want to find it out. So classically, you have to like there are a lot of methods in there. You can go either linear search or like sorry, I forgot a lot of searching algorithms. A quick short and all. Sorry, so that was sorting actually. I'm really sorry for that. So there are in classical we have like a lot of searching algorithm which can go for order of n to log and also those things. So the idea is like what you'll do, you'll give the input. Suppose 66 was a number which you want to find. You'll put into some black box, or you can say as an oracle in quantum, we generally would define as oracle, okay? And this black box will do what it does, it will put an algorithm to find the number 66, okay? And the output it will give, okay, the particular index 7 is the space or area or index where I'm able to find the number 66 there. So this is a problem statement is like you have to find an element. Okay. So that's what how we generally search in a classical part. And if I have to talk about this comparison, you can see if I have to search this number, since in this part we are just dealing with the linear search, okay, not something other. So in the classical, if you have to search a number, it will generally go like one by one. Like that means it will go step by step. Like first it will go for zero index, first index, second index, third, fourth, till the last index, till it's able to find the number which is exactly it's looking for. So classically, it will able to find in order of n, okay. But in quantum, to find the same number, it can find in a root n itself. So that's where we are getting a quadratic speed up here. And this was a biggest breakthrough back in 90s itself. And it was the first algorithm to find a number, like it was the first one. So you can easily see for a comparison for a time complexity how it works, like since you're already aware of it. So if you have to find a number and like if you want to find a number in a classical via linear search operation, so it is going linearly, it is growing, correct? As the input sizes increase, the running time also it grows linearly. But for the quantum, you can see I'm able to find the same element in root n time itself. So you can easily see how quadratically speed which we have observed. That means like here I have given a small example, like to search a number list of 100 elements you have to go for 100 times, right, in a worst case classically. But in quantum we just have to do square root of 100. That means within 10 iteration, 10 circuit, or within 10 times, within 10 runs I should say, you're able to find the number. So that is exactly a quadratic speeder which we have got into the quantum just to find the same number, okay. Now the way global searches works just like classical itself, but we have to design our own black box here, our own oracle here. Like so in quantum, we like instead of saying as a black box, we generally refer to as a term as an oracle here every time. That's the notation we generally follows here. So we have an input, we have an oracle, and it will give you the output. So Grover search is like it's not like you're actually finding something. It is like within this black box itself, the condition is like that number is already there, and you have to find it out. Okay, it's not like if a three-digit number in input is like for three, and you want to search for a five, that doesn't work. The length should be same. It should be same. Okay, so if it is like input is of 3 bit, so within this black box itself, that number is already there. You just have to find it out. Okay, that's what the black box is, and in the output it will give you that number which you're looking for with certain with certain probability along with it. Since we in quantum, we have studied everything, it's a probabilistic in nature, correct? So this Grover search exactly did the same way. Like, you have your number which you want in the black box, it will give you that number along with its certain probability like 95, 96, 97, but based on how beautifully you have designed your oracle there. Okay, now the idea is like, in quantum, when we have number of qubits there, we put edge gate there, correct? So what we'll get? We get all the numbers in a superposition state, correct? That means all the numbers which you're having, they are having the same amplitude, right? So in this is one of the small example I've taken. Like, this is number from 0 to 7, right? That means I'm having a 3 qubit, correct? 3 qubit. I have applied edge gate on all the 3 qubit. I have got all the state from 0, 1, 2, 3, 4, 5, 6, 7, correct? And the moment I apply an edge gate there, what I will be experiencing, that all my states from 0 to 7 are in a superposition state, and they are having the same amplitude, which is nothing but 0.125. Okay, this is how you do the initialization part. And the idea is like, suppose this green index, the green bar which I'm having, it is index 4, right? I want to actually find this number. So how to find that number is like, that's called amplitude amplification method is there. So this method, what generally does is like, it will actually going to increase its amplitude, okay, for the marked element which you're looking for, and decrease the rest of this element amplitude. If you can see the comparison here at that in the left side, it is like 0.125, right, for all from 0 to 7, correct? But on the right side you'll see, except 4, like from 0 to 3 and 5 to 7, these numbers, their amplitude got reduced from 0.125 to 0.05. And for the marked element which I was looking for, its amplitude got doubled from 0.125 to 0.30. So this is the idea of Grover's algorithm. Like, the element which you want, its amplitude should be increased, whereas the amplitude for rest of this element, it should decrease. So that exactly this amplitude amplification method does. Okay, now how this amplitude amplification procedure is there, how it works, in step by step I'll go through it. So first thing I have told that we have to make all my state into superposition state. That means since I have a 2 qubit, okay, 0 0, I'll apply 2 edge gate on both the qubits. I'll get all the 4 states 0 0 0 1 1 0 1 1, correct? And all those 4 states will be having a equal amplitude, half, or I should say probability. Okay, probability here. So in the amplitude part, you'll see 0 0 0 1 1 0 1 1, correct? It is having amplitude of 0 0.5, 0 0.5, 0 0.5, 0 0.5. And when you do the square of this one, you will get a probability there. That is 0 0.25, 0 0.25, 0 0.25, and 0 0.25 there. Okay. So this is how theoretically you can understand how it is working. But at the same time, on the right side, I have shown how you can visualize it also. That means if this was my state, x and y plane, a perpendicular and a here, this size 0 is my initial state. Like, this size 0 is half, is the amplitude for all the states. So this state is located somewhere in this region. Okay, as of now I'm not finding any number. I have just what I did, I have just initialized all my state. That's it, nothing more than that. Okay, and it is having some angle also, theta. And what I want to do, and this is side, like, see, there are other ways to also do it. So this is one of the outside, or sorry, output which I thrown using a density matrix operator there. So density matrix, I don't know whether I've studied or not. I'll just give a small uh, idea. It is actually nothing but a outer product. Like, you have cat 0, okay, do the multiplication with bra 0. So that time you will be getting a 2, like a n cross n matrix. Since this is a 2 cross 2, correct? Since we have a 2 qubit, I am getting 4 states. So exactly 0. So this state is 0 0 0 1 1 0 and 1 1 there. If the state is 0 0, I'm getting all the 4 state. If the state is 0 1, I'm getting the 4 state. So these are its amplitude mentioned. For a state 0 1 0 1, sorry, 0 0 0 1 1 0 1 1 with a dimension of 2 cross 2 here. Okay, so this is just the initialization part here. Nothing did, nothing. Just have a 2 qubit gate, sorry, two qubit, applied a harmonic on both the qubits. That's it, nothing more than that. Now the idea is like, once we have all the state in a superposition, once have all the state in a superposition, now what I want to find a particular element. So this is a 2 cross 2 2 qubit example. I want to search an element 1 1 here. So what I have to do, what I'm going to do, I am going to introduce some phase towards this particular element 1 1. Okay, that means I'll show you how it will happen, or like what is the reason behind it, I'll tell you. So first I'll do, for these are the 000110. See, these are the number I generally consider as an unmarked element, means I don't want to search the element. Okay, 1 1 is the element I generally say as a marked element, means this is a number I'm actually looking for to search into my database, or yeah. So this was the first stage, right, where all my states are in super state from like 00011011, correct? Now, once that part is done, I'm introducing a phase to my marked element 1 1 here. That's why you're able to see it got shifted like x and minus y plane here. It's in the fourth quadrant. Okay, like I just say, take an example here. Fourth quadrant. So as of now, as of now, I'm not seeing any difference. And this is just a phase has been introduced. That means the reason why I introduced phase, because this is the number I was actually looking for. That's why I have introduced some phase towards this negative phase, so that I can it can differentiate between this is the marked and how I can differentiate from the unmarked element there. Okay, so 000110 unmarked element, 1 1 it was a marked element. So I just introduced some phase towards it. That's it. Okay, so even in its amplitudes, if you see its amplitude for 000110, nothing, amplitude remains same, 0 0.5, 0 0.5, 0 0.5. Here also amplitude remains same, 0 0.5, but only a phase has been introduced, nothing that. Okay, nothing more. And if you go for its probability, again 000101, if you check its probability, you won't see any difference. All at same 0.25, because once you do the square of this one probability, if you do this modulus square of this one, you'll get exactly 0.250. That's the probability of it. So as of now, I have just introduced a phase to my marked element for a state 1 1. You can try, I'll tell you how we can mark or how I can add a negative phase minus 1 minus to this marked element also. Now once that part is done, then what I have to do, there's something called mean inversion. Means like, I'm going to invert all. I'm going to perform the inversion around the mean for each amplitude. What it mean is like, this part I have shown. So, okay, sorry, slide was skip. Yeah, invert all the probability amplitude around the mean, means, so this was a 0.25, like for 000110, all these three having the same amplitude, correct? 0.25 in the last slide. So sorry, probability 0.25, 0.25, 0.25, 0.25. And this was a marked element which is having a negative phase, that is minus 0.25. And since we have four elements, correct? So what I'll do, I'll do the mean of it. But I got 0.125. Now what I'll do, for the state 0 0, okay, I'll do 2 dot, that is multiplicate with mean of 0.125 minus of 0.25 here. Okay, similarly for the second element, third element, fourth element. So what this step is doing is like, it is actually changing the length of your marked element as well as unmarked element both. It is doing the both for it. That means in the right side, if you see, this was the part, like if I show you, this was the part where I'm having all my states, all the four states with positive phase, right? Plus 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 plus, right? But when I introduce this negative phase of for my mark state 1 1, there you see only that that marked element 1 1, it got changed here. It got like negative phase, or actually reflection. First it did some rotation, then it will be some reflection about it, about the mean. Okay, so the marked element which was here 1 1, it got shifted or transferred to this area, whereas this area still contained my rest of this unmarked element, that is 0001 and 10. Okay, so again, so this is same thing, amplitude 0.5, and there's a probability. So as of now, I have just introduced a negative phase to my marked element. Now once that part is done, because of this, 2 dot mean minus a of I, that means for each element, what it this does is like, it will suddenly going to increase the amplitude of your marked element. Okay, like when you do this operation, what you'll observe, this rest of the element which is having some amplitude, it will go to shrink, and this minus which was here, this minus and this minus, it will act as a plus. Once it act as a plus, then you will see it got changed plus, and its amplitude got increased up to 3/4 of it, whereas previously it was all 0.125, now it got increased there. So once it got increased, you'll observe it here. This was a marked element, correct? In the previous, the length is all same, correct? Length is all same, but because of this mean inversion theorem here, or amplitude amplification method, its amplitude got increased, almost got double, you can say, and the rest of these elements, their amplitude got shrunk. Okay, so this shows me that the element which I was looking for to search into my database, it actually got increased from like 0.125 to 0.7. It almost got to 3/4. It got increased 3/4. In the right side, if you see, this was my initial state size 0, right? And this was the part I generally consider as a bad state, and this I consider as a good state there, because the idea is like, the good state or the good element or the marked element, I want to make sure it should get closer and closer and closer to this area. Okay, and you can see in the other side also, like, instead of going to this region for a marked element, you can also expect like the unmarked element should go closer to this a perpendicular region also. Okay, so in the initial part, like when we having a superposition state, so this was theta 0, right? Then I have introduced a mean inversion. So that means that particular element with the same theta angle got transferred below the x-axis. That means it will be in a fourth quadrant, x and minus y plane. Okay, so now what I'll do, because of that mean inversion, that is 2 times mean of each element there, this theta 0 plus theta 0, it will get add up, it will be like 2 times of 0, like 2 times of theta 0. So you'll see now the same angle which are theta 0 plus theta 0, it is equal to 2 times theta 0. The initial state was here, it got crossed this area, like it got, now it is getting a little bit closer and closer. Okay, so this is, we generally refer the term as a reflection. So I did some reflection of the same length which is here, like theta 0 plus theta 0 here both. So it got to 2 times of 0, 2 theta 0. And now this is my next state, that is psi 1 is equal to s of initial state psi 0. So this s and o, this is mentioned here. This is nothing but I have applied some operation, unitary operation, onto my initial state here. So that's why now this is my psi 1, which is my next state which I have worked on. So with this is a small example, like it is already came a little bit closer to that region. So once I do is check its amplitude for 0.0, 0.0, 1, 1, 0, 1, 1, you see it's 0.0, 0.0, minus 0.0, and minus 1.0. So the marked element which is looking for, it is having minus 1. And when I do its probability here, I got a 1, that means 100% probability, that 100% that the marked element which I was actually looking for a 2 qubit, it is 100% successful. So this is the idea behind Grover search. Like, first, all your state is in a superposition state. Okay, then I have to apply this mean inversion or amplitude amplification method, where because of this formula, 2 times mean of your element, do that twice, and its length will going to increase. At the same time, in the right side, you can easily visualize also how it is changing step by step. This is the density matrix, not required for now. Yeah. So the final amplitude after doing this mean inversion here, like after this iteration, the probability distribution will be 0, 0, 0, 1. That means this one is like for a marked element 1, 1, which is having like a probability 1. It is having a probability 1 that I am able to search this element. Okay. Now that is was the case for a 2 qubit within, that means with a single iteration I was able to find it out. Okay, but as my size of my state it get increased. Just a minute. Yes. So I was saying that in the previous example which I shown here, it is for a 2 qubit, correct? So within one just single iteration, I got the marked element with the 100% probability, right? But if my size of my database, if my size of the qubit, if my number of qubit increase, like from 1 qubit, 2 qubit, 3 qubit, 4 up to n qubits, there you will observe that it's not just a single iteration. You have to perform root n iteration there to find that marked element with more probabilities there. Though even if you apply less iteration also, you will able to find that marked element, but the probability of that one, it will be more only, but not that much compared to the rest of this element. That means there is some overlap will definitely will be there. So the idea is like you have to know exact number of iteration to find it out. And how we came to root and time in the coming slide I will explain. So in this example, like I have shown it here, like we have a 3 qubit system, right? I've got 8 states. 4 is the number which I'm looking for. So this is the first iteration. This is the second iteration. First, in this state, in this image, first I did this, flip it, okay? Negative phase I've introduced, negative minus to the state 4, okay? And then I did the mean inversion. Its amplitude got increased again, and the rest of this element amplitude decreased. Now, if at the moment I performed one more iteration here, same again, this will flip it back. That means again apply the negative phase, and this time increase its amplitude again, and its rest of this element's amplitude will again going to shrunk. So within this two iteration for a three state, like where you're having 8 elements, within just two iteration, I'm able to find my marked element with a very good probabilities there. Okay. And what if happen if I did one more iteration then? So this is a perfect case here. Like till second iteration, if you see here, I was having a very good probability of a marked element, right? But the moment I did one more iteration there, like I did the negative phase, you see its amplitude, the marked element which was there, it suddenly got reduced little bit, and the unmarked element which was here, which I was not looking to search, their amplitude little bit got increased here. So this is the difference, like why you should know the exact number of iteration, why not more than that. This is a perfect example why. And at the same time, if you can even in this case also, yeah, in this case I'll try to explain. Suppose this was a marked element, right? This is just for a two iteration, correct? If it was three iteration, for a three qubit, I'm just talking for three qubit. For a two iteration, it will be somewhere close to this, okay? Somewhere close to this. But the moment I run it for one more iteration there, then the same vector, it will it will be cross this particular region. And the moment it will cross to this region, I have already missed my good state or good area, or I should say a state, a good state here, where I should have stopped there. Now, once I have crossed this area, that means I've taken one more iteration. After this, I take one more iteration. It will go like this: circle, 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 and after certain iteration, it will it will come back to this particular area where all my states were in a superposition state at the initial level. So that means all my operation did, which I performed there, it is nothing, just wasted. Okay, so this is the reason why you should know how many iterations you have to run your Grover's algorithm. Now, how to do it? That's the part I will be talking now. So first, amplitude amplification, it has two parts. Like it is an oracle, that is UF I'll talk about, and U phi, that is the diffusion operator. That means it inverts amplitudes about the mean. So these two blocks, or these two, I should say, oracle, we should run root n times. That exactly I have mentioned in the bottom. That is repeat root n times here. This n is nothing but number of states. Okay, so if small n is equal to 3, so capital N is 8 actually. So I have to run root 8 times if we have a 3 qubit. Once I run around root n times, okay, then I will find that the probability of a marked element, it will be up to like 96%, whereas remaining 4% will be distributed between the remaining 7 elements. So that's how this amplitude amplification method works. So first, this is my initial state, okay, like 0 0 state. You can also make it to 1 1, is up to you, but this is a default one. Okay, once you have, then we apply an H gate to get all the states in a superposition. Like for 3 qubit, get all the state from 0 0 0 to 1 1 1, and then apply this oracle diffusion operator, and just run this only these two parts n times, and in the end do the measurement, and you will able to get your marked element there. Now, how to develop the classical function for that? Classical function is like, if the input x doesn't satisfy the criteria, means like if I want to find a particular number and if it doesn't fit what exactly want, I will put it as 0, and if I got that number, then I will give it as a 1 there. So in this one, I want to look for a number w, like 00. So output say yes, I have got it, yes. And for other thing, it doesn't satisfy the criteria, so it has got the output 0. This is how the classically we generally see. Same way also quantum also we have the same function also, but how to solve it, that matter is little bit different. Now, this is the first part where we'll see how you can design your oracle to find a specific number, whether you want to, since this is for a 2 qubit example, so how to search for 00, 01, 10 and 11. Okay, so to, to search for number 00, what I have to do, like I have introduced x and x here. Why introduce x is here? Because in the bottom this blue circuit or a blue gate which you see, it is nothing but is equivalent to control z gate here. So the idea is like, if this is a z gate here, what it does, like for a state 0, it doesn't do anything, correct? For a state 0, it will remain 0, correct? But if the state is 1, what it does, it gives a -1, correct? That negative phase or the phase is being introduced, right? So exactly the same gate control z gate we also have to use into our oracle here. And the reason why we put x here, because of this x only, this control will going to active, correct? Because to otherwise if there is 0, then this control z won't work, right? And to make sure it should work, and this z only going to work if this input, if it is 1. If it was 0 again, then this control z won't work. So to find a like marked element 00, what you have to do, apply an x and x. So now it's been converted to 1 1. Okay, once it's been converted to 1 1, that means now this control will be active, and because of this one, we will be adding a phase of -1. Once this phase is being introduced, -1, then I will append x and x again. So I will be getting back to the state 0 and back to the state 0. The reason why we did, because the only thing is like we just have to introduce a phase to a marked element. That's it. That is the only reason we have introduced x before and x after. In this case, this is for a marked element 0 1. So 1 will be on top, 0 will be here. So this is the first qubit and second qubit. For 1, I don't have to apply any x gate, right? Because since by default, because of this 1 itself initial part, this control will be active default. And for 0 to work to add some phase, that's why I've added a x gate here. Then z and x. So x, z, z. So x, z and x here. In this case, I was looking for a 1 0. So this 0 will be here. So again, it will convert to 1. Control will be active here. This one will go here. And a phase is being introduced for this one also. And if my already state is a 1 1, so in that case, I won't be introducing any x gate before and after. So this is how you can design your oracle to find any number from 0, 001, 1011. These are the 4 cases I have explained. Similarly, you can design it for a 3 qubit also, 4 qubit also. Okay. So the whole algorithm work is like, step 1, you have to initialize. Okay. Step 2, like Grover diffusion operator, which consists 2 times, like one is oracle, one is amplification. This was oracle where we were doing this inversion, and this amplification means it is increasing the length or the amplitude of a marked element. Repeat this whole process, oracle and diffusion, root n times, and once the number of iteration is done, then simply do the measurement part, and you're able to see the marked element with a very good chunk of probability, 96% for a 3 qubit. Now this is the code for it. Like I'll come to later that part. So if you have to introduce like 00 by default, so just say I want to have 2 quantum register, 2 classical register, and I'm just combining into one common object called circuit. And once that is ready, I will apply to H gate. So circuit.h, apply Hadamard gate on Q0 and Q1, Q0, Q1. You'll get all your state, and then I'll be applying a control Z gate. This is the called as a barrier gate. So this barrier is not that much important, but it actually help us to understand, okay, this part from this to this, I am trying to implement a oracle part. So that's how it actually helps us to visualize much better. Though even if you don't use, it's up to you, but sometimes it get very much clutter when a circuit get humongous, quite big. So to differentiate like oracle, this particular function, second oracle, third oracle, this oracle that time is very much helpful. So what I did, I just wrote circuit.barrier, quantum resistor 0 as well quantum resistor 1, circuit.cz, control Z applied here, control this qubit 0, qubit 1, circuit.barrier again, q0, q1 again here. Now this control Z, it has what it is for us marked element 1 1, it has a negative. That's it till now, that's it. And now this amplitude amplification method does is like it does the 2 times mean minus each and every element. So this gate H gate X control Z S X and H, this will actually does the mean amplitude like amplitude amplifications part, and in the end do the measurement. Since for a 2 qubit you just have to run a single iteration and you'll able to find with a 100% chance or like probability 1 of that marked element 1 1 in this particular case which we are working on. And then I have this backend like say DM simulator is like we run it into this quantum simulator QC which we have. So this is the code of that particular simulator. So we have used basic air get backend DM simulator. Choose a circuit, this whole circuit, backend this DM simulator. Options is like if you want to introduce noises also, like how one particular noise impact your particular circuit. Noise in the sense like initialization error, rotational error, thermal error, depolation error. There are certain 4 5 more type of errors. So in QC we have given that option how you can see your particular set of error actually impacting or how much it is deviating from the actual simulated result. So that kind of like simulator is very much helpful if you want to do the proper comparisons part. And then I'm doing the data to ensemble probability. That means now job is ready. I want to see in the histogram. So that's where I wrote data dot ensemble probability here. And this is how you can run on a QSIM, like select plot, choose the backend Paramutkash or Shakti. This is one of our HPC here in Bangalore and one is in Pune. Run the circuit, run this whole order of root and times, you will be able to see. Now, this is the part I'll talk geometrical explanation here. Okay, so the idea is like this is my bad state where I want all my unmarked elements should be remain in this area and all my good state should be come to this part, and that's how I've divided my psi state, that is alpha good plus beta bad, to differentiate between the 4 state which we are having. So bad state means the unmarked element 000110. Okay, that these are bad 1 by root 2, 1 by root 3, 00011. This is like once you like divide this good and bad, you have to make sure it should properly normalize also. Okay, 1 by root 3, and these are good with the 1 1. So after the first application of H to every qubit starts with the uniform superposition of all the state, this can be written as psi state, which is bad, and means the 4 state which we are having, that is 2 raised power to 4 minus 1, because m is my 1 because I want to search only a single element. So 4 minus 1, 3 by root 4. This is bad. Since I have a 1 good element, so 1 by root 4 good. So that's how you can divide. Sorry, you have to normalize your good and a bad state into a psi 0 state. This all means we're having this all like good and bad state together as of right. It's the starting state. And the idea is like I want to go to this particular good. Okay, so that is sine. I have to like theta should be sine because that is sine and this is cos here. So sine is like G is the good. Okay, the single element which I was looking for 1 1. Psi 0 where all my initial state is there. So this is where I am doing the inner product there. So what it does is like only for the good element which I have, okay, it should be equal to half. I got it half, and for a cos, it is remaining root 3 by 2. And once you have that, since I have to sin theta is equal to half here, so theta will be pi by 2 here. That's why I have this pi by 2. So like to maximize the probability of measuring the good state G, we need to balance it. That means sine square 2k plus 1 theta sine k sine square 2k plus 1 theta. Now why you must observe where this 2 came from and what is this essence of k means and why is 1 here. One is like default, like when you go through one iteration that is there. This two is actually coming from, since you have this rotation and a reflection operator, that is I have shown that is 2 theta 0 was there. That's where this 2 came from. Default is 1 because you have to run at least single iteration there, correct? After this having single iteration, how many more you have to go for it? That's where this 2k plus 1 is actually coming from. So once we have this 2k plus 1 theta, it is equal to pi by 2. Simply get k is equal to 1 here. Okay, so for a 2 qubit, it is saying that just with a single iteration, you will able to get your marked element with a 100% chance. But as your size of your qubit increase from 2 qubit to 3 qubit, 4 qubit, the the number of iteration, which is nothing but it is k, which is mentioned here, it will also going to increase from 1 iteration, 2 iteration, 4, 7, 8. Based on that, the success probability of your marked element, if you instead of having the, like when we go for a 3 states, the success probability of a single element, it is 96%. Okay, after having more elements there, like for 4 qubit, 5 qubit, 6 qubit, at that time the marked element probability, instead of having 96%, it will go reduced slightly, like 91, 84, 80, 70, something like that way. It will start reducing it, whereas the unmarked element which is having, their probability, it will go so less, but when you sum it, it will equivalent to the one itself. That's how you can understand geometrical explanation at the histogram also changing side by side. Now, the application of Grover's algorithm is like, you can help, it will help in like searching for a marked element in unsorted data already done. It can also help to solve NP complete problems like SAT problems, and even it can help in cryptography things like, it will since we already know it gives us a quadratic speed up. So for a brute force attack on a cryptography hash function and encryption scheme also, these are the few domains which you can explore, since I'm not from like cryptography domain, but I haven't tried it as well, but you can try it. Yeah, now I'll just go to our Curious platform. Since you're already aware of how to use this universe, so I'll just try to go to this my algorithm sections. I want to, let's say I want to okay, just take it first, two queries. Okay, I'll show you the difference.
Sir,
uh,
actually, you have to unshare and uh,
okay, sorry. Yeah, okay, now it's visible, right?
yes, sir.
Okay, so in this case, Grover's algorithm, I am taking the example for a 2 qubit to find a marked element 1 1. Okay, I'll just load circuit here. I'll show you some difference. Wait. Yeah. So see, when it comes to 2 qubit here, this is the oracle part and this is the diffusion part. In the PPT, I have shown you that we are using a control Z gate, correct? But that control Z, which was Z here, it is equivalent to applying H, X, and H. So H, X, H is nothing but it is equivalent to Z gate there. So either you can use like this way, or you can straight away use this control Z gate also. This no worry, you can directly use that one also. So you'll observe it that with just single iteration, this oracle and diffusion, with just single iteration one, I'm able to find the marked element one with a 100% probability, right? This is one of the case. At the same time, if I'll go for to search the other elements, like for a 3 qubit, I'm just talking for 3 qubit, I'll go for this number 111 triple, okay, triple one. And if I load the circuit here, you'll see, though I have to run two times, right? This is oracle diffusion. This whole is my one block, okay, and then again oracle and diffusion second time. You'll see that this time for a 2 qubit it was like 100% chance, right? For a 3 qubit it got reduced to 94%. To find the same, like there it was a 2 qubit double one, I have to search. In this case I have to search for triple one, right? So you can see how my probability also got decreased. At the same time, if you see the other elements, yeah, 0.7, there are some probabilities associated with the rest of this element also. How, so that's how you can see, like after doing certain iteration, the probability, though it was like for 2 qubit it was 100%, for 3 qubit it got reduced to 94%. And as my size of the, as my number of qubit increase, number of iteration also going to increase, and the success probability of that particular element, it will slowly got reduced, because now my state space getting bigger and bigger. So this is one of the like problem with the Grover search, is like it is giving the output into a probabilistic nature, not in a deterministic way. Okay, now this is the case like for I have a single sorry, I run it for two iteration, correct? And I was only looking for a finding single element. Now in the cases I've told you, like that when you apply oracle, the state, it will be getting a negative phase, it will add it, right? That is the, in the ppt I've shown you. So how to see that negative phase? So I'll just click on state vector here. Okay, and just click on debug method. Okay, so now I'll go to step by step each iteration how it is evolving. This is the first iteration, right? You can see all are my states, correct? From 00, 000 to 111. All the states are in a equal, with equal amplitude, like it's same. And the moment I pass it through my oracle here, okay, since I was looking for 111, you see the phase that is negative, it is being introduced only to my marked element. Whereas rest of this element, if you see, they all with a phase angle 0, and the marked element which I was having, it got a phase of 180 degree. Okay, and the moment I just pass it from a first diffusion operator, you see this was a marked element, right? So that particular element, its amplitude got increased. Okay, whereas rest of this element, their amplitude suddenly got reduced. Okay, and everything having a phase of 180 degree, right? And once you do its a probability, then everything will change to the positive also. And then once again, if I apply the second time oracle again, so see this time what is happening is like I have got a state 111, okay, positive. So this element negative again, the amplitude doesn't change anything. But the moment I run it for one more iteration here, you will be able to see that the marked element which I was having, it got increased to 97, whereas rest of this element, their amplitude got shrunk from zero, like up to 0.88, something like this way. And then in the end, I'll do the measurement. You'll see around 97% chance. So it's like 97, it's the close number, or 96% is the close number. You'll get it for a marked element. Now the question is like, is there a drawback in this gross algorithm? Like probability is the one thing which I've told you, but it's not a drawback. Like, but people generally explain how to find a part element, correct, on a single element. But what if I want to search how, what are the steps we have to add if I have to search one more element there? So what you have to do, like instead of having single oracle, okay, just add a one more oracle there. Like just add one more oracle, first the other element, second oracle diffusion, again oracle diffusion. In this method what you will see, instead of searching for a single element, now you will able to search for two elements there. Okay, so let's take a small example how to do that. Okay, I'll just take for other element. So this is how you can see. Now I have two oracles, correct? Because now I want to, since I have two oracle means I want to search for two numbers, correct? So this was number I was looking for 010, correct? This is 0, this is 1, this is 0, right? And yeah, this is the other number, triple one. So now I'll just triple H. I'll just put as a custom. I'll write as a like Oracle RO. Okay, I'll write as ROO. Second, click on save. Okay, sorry, limitation is there. I have to remove this part. Delete gate. Okay, RO is there. So I just have to introduce one more time. Delete gate. So something different must be there. Okay, I'll just create it once again. Just put it X here. So you can see like it's not like you can just search a single element, but if you append your oracle like the element which you're looking for 010 also within the same method, you can also find more than one element also. So this is one of the example I've given. There's something wrong. Oracle. I guess I might be doing something wrong, but the idea is like since I was looking for two numbers, so oracle is already done. I guess for a single, if I would do a single time, two oracle, one diffusion, and if I remove everything, this part, if I just delete, yes, right. See, like as I told you, know, like since instead of searching for single element within 3 qubit, I was having to run two times, right? But as my number of search element got increased from one element to element, then my number of iteration will also going to reduce further. Okay, so this is the reason, like this is one of the example you can understand for the same 3 qubit only. Previously, which I was running for a two iteration, now within just single iteration, I was able to find that marked element here. So it is a 50% and again a 50% here. So that's how you can like find multiple elements within the Grover search. But the only condition is like instead of running root n times, it will be reduced. And how it will be reduced? There's a formula for that one. Like if you're like in the PPT, I haven't mentioned that formula. There's like half log m by n. M is number of marked element divided by n. M is so as the number of m increases, the number of iterations should also start reducing it also. So this is how you can understand like for a Grover cell algorithm, like if you want to find for more than one element also. Now in this case, like this is the algorithm which I've shown you for a like which is in probabilistic in nature, right? But what if you want a deterministic, like if I go for one more example here, let's just take for other 1010. Okay, for a 4 qubit load circuit. See, for a number 1010, I have got a 96% probability right here. But why? 96%, why not 100% there, right? So we have developed our own algorithm. Actually, one of my colleague developed this particular algorithm known as a deterministic quantum search. Means like it will again work as same quadratic speed. Quadratic speed. It will again give the same thing, but this time it will give us certainty. Like I mean, instead of getting some probability like 96, 97%, it will give a 100% chance. Let's say I'll take a small example for a 3 qubit, okay? Because in the Grover search, when we are running for 3 qubit, to find the same element 111, I got a 96, 97 as a probability there, as a sorry, percentage. Sometimes I got flip it always. Load circuit, load. So see, the moment this time, this is another method to search a marked element. In this, in this, I'm just using a one additional qubit, okay, using rotational gates, same oracle method, okay. The only difference, like the last, this is ancillary qubit which we have introduced, okay, and because of this particular style, this particular algorithm, we are able to find the marked element with a deterministic, with a 100% probability, not like a probabilistic in nature, but it is like probabilistic with a proper deterministic, like 100% chance. So this is one of the algorithm which we have like developed it. So I want you to like further explore this particular DQS algorithm and see how you can use this algorithm into your own other application where you want proper deterministic instead of having some certainty, like proper 100% chance that you want to look for. So this algorithm you can like refer also. Yeah, that's it. Any questions?
Yep.
I'll just check the comment sections.
Sir, shall I read out from
Yeah,
420?
sure.
Yeah.
I'll
What
just
is the purpose of
420.
amplitude? Yeah. From the top we are coming. That will be
Okay,
easy.
what is the purpose of amplitude amplification procedure? Okay,
Right.
I'll just answer it. The idea of amplitude amplification procedure is means like since when we in the first state when we are getting all the state in an equal superposition state, right? That is the first thing. But
Oh,
now I
oh,
want to increase that amplitude of that particular marked element. That's where I introduced that formula called 2 into mean minus A of I means every single element. So because of that particular amplitude amplification method only, this amplitude of the marked element it is increasing, whereas for rest of this element it is got reducing. This is the purpose of amplitude amplification. That means you have to increase the amplitude of your element with like more than like instead of being a superposition state, it should be increased, and for rest of this it should reduce. This is the purpose of doing amplitude amplification procedure. How do we know that state 11 is the target state to be amplified? I mean, we don't know the location of the search element. Okay, this is the general people get confused about when it comes to location wise. In classical, we have a array, correct? 0, 1, 2, 3, 4, and in that we have added some elements there, right? But the way quantum work is like in quantum, your element is already there into that particular space there, right? So we just have to increase that amplitude. We just have to find it out, like its amplitude, like its probability should increase. Whereas in classical, it's like it could be or it could not be, correct? But in Grover, it's like the element is already there. Okay, the element is already there into your state space. You just have to find it out, or you just have to increase its amplitude. That is the only difference between classical search and the quantum search in this one. So in this one we are not finding its location, we are just finding the element is already there. We are just making sure that we have to increase its amplitude. That's the only difference. If a search element is 01 procedure means oracle will change, right? Okay, in our search element is if a search element is 01 procedure means oracle will change, right? Yes, if your search element is 01, based on that only you have to change your oracle. That means now you have to, on the first qubit you have to introduce x gate, okay, control z, again x on the top right side. From the last qubit it will be remain nothing. So based on your oracle, sorry, the element which you want to search, your oracle should also going to change. VQL algorithm I can explain maybe like some other time. Just ping me. I will. I will definitely going to explain VQL algorithm also. I don't have any issue because previously I have worked on this VQL algorithm a lot and QA also those things. So I don't have an issue. I can explain it further later also.
Yeah,
So
yeah.
do
Maybe
you put another?
we can invite sir in the quantum computation course. At that time, some of the algorithms will be discussed. We'll look
Okay,
at how they can be implemented on. Once
universe.
you know how the algorithm is explained, then
Haha.
it is very easy to explain the implementation part, right? Yeah.
Correct, sir.
Sir, you
Correct.
can go to the next. Yeah.
Okay. So can we search any number of element using this algorithm? Again, the only condition like you can search any number, but that number should be into that particular state space. Means if you want to search a number for a 3 qubit, like or should say 3 bit, okay, so you should introduce a 3 qubit first, not a 2 qubit first. Okay, so that's the only difference. Like want to search, make sure the length should be same. If you want to search for three element 111, then your initialized qubit should be exactly triple, like triple zero, apply h, all the zeros to up to one. You will be able to search. It's not like you want to, to search for 4 digit like 1010, and your state space is like up to only three triple zero. It doesn't work like that. How does iteration implemented into the circuit? Okay, when we come to iteration part, in the last slide I have talked about, it's like 2k plus 1 theta, right? So that exactly the expression came from. Like there's again, if I have to explain the iteration, but it's again quite some time it will take. But I'll just say, if you want to know the exact number of iteration, it is nothing but it is equivalent to floor of half log m is number of element divided by total element. That's it. If you're able to solve that particular expression there, you will get to know it is equivalent to root n itself. So that's how the number of iterations can be implemented. How to use this algorithm for QML? Again, I'm sorry for this question. Actually, I'm not from QML background, but I'm really sorry. But you can definitely give it a try. What shall we do if we have multiple elements to be measured? And what will be the distribution of probability? Okay, if we have multiple elements to be measured. Actually, we can't measure multiple. I mean, actually, you are actually okay. When we say multiple elements to be measured means like we have a 3 qubit right already, correct? So just apply 3 measurement gate. So in that case, even like you're able to like what to say, do the measurement of all those elements. Not like you're doing a measurement for a specific element. You're actually doing the multiple elements. You're actually doing the measurement for multiple element itself. And based on this distribution, like it will reduce as my number of marked element within a same state space it got increase. If searching element is not there, can we use this? If searching element is not there, can we use this algorithm? I don't think so, because since this whole idea of Grover's algorithm is like you have to search that particular element. But yes, instead of saying a searching element, you can use the other that diffusion operator which we are having, correct? So that diffusion operator, its job is like just to increase it. So that particular segment, you can use it for other algorithms also. If search element is not there, how will we do so? Then no amplification then for anyway. So by default, the element is there and you are actually searching it. So amplification method is actually required for sure. Okay, so you took theta is equal to pi by 6. How can we decide that value? Okay, the reason why we came to that particular value is because in my when I've mentioned that I have four states, correct? One is a marked and three is the unmarked, correct? So what I have mentioned that sine theta it is equal to a good this measurement along with the all states, correct? So it is like only one element I was looking for. That's why I got the value like sine theta is equal to half, theta is equal to pi by 6 there. But if my number of good element is increased, then my theta value will change. So it's not like I have fixed my theta value, but because of single search element, my theta value was there pi by 6. But if I have more good elements like 2 out of 4 or 3 out of 4, then my theta value will eventually going to change there. Yeah, yeah, that's all the question I
Thank you so much, sir, for your valuable time and a very short notice. Thank you so much for taking the
No,
session and
it's okay. Actually,
very
I'm
quickly
constantly
going.
giving this kind of session. Actually, before this
Right,
session, actually 2 to 4, I had to give another session in one of the Kerala colleges there. So 2 to 4, I
right,
was giving there, and then 4 to 5, I have to give it here. So I'm like now used to these kind of sessions every time. So and
right,
the in the next week also, like one university, Kannur University, there I have to give a session. Then next week I have to go to this RIT Chennai college is there. So we are like now used to this kind of short notice sessions and all, totally comfortable.
right.
It's not a big issue
Thank
for
you
me.
so much, sir. Actually, one of the speaker could not come at the last moment. So
Okay,
that's where
okay,
in the
okay.
morning I contacted Santosh sir from CDAC
Haha.
because we were trying to interact. We are trying to collaborate with CDAC Bangalore, MNIT Jaipur. I will try to
Okay,
have some
yeah.
Q
Huh.
inverse workshops and all. Right. So thank you so much for your valuable time and participants have understood. Actually, getting hands-on on a full algorithm was a good
Mhm.
experience for them. And thank you so much for being with us. We'll continue to the valedictory session, sir. We have concluded. In fact, your session was the last lecture for the 60th lecture, you would say. These are
Okay,
two
okay.
courses, QT-03 and QT-04 combined,
Okay,
basic
okay.
programming and basic technologies lab sessions. So mostly the sessions were hands-on like yours. So hopefully you have understood how much is the maturity level of the participants also based on the questions that you have
Yes,
got.
yes. Actually, I love to answer this kind of question, to be honest. I'm very much happy to answer this. Because when I
Right.
was like 2 years back, I also want some of my question to be like resolved. But that time we don't have that this many resources at that time.
Correct.
But now
Correct.
we have, like,
Correct.
so I'm very much happy to answer this kind of queries.
Thank you so much, sir. So we'll continue with the valedictory session. You can continue to be here to listen to the participant feedback, but in case you are occupied with something, you can exit. Yeah, thank you so much, sir.
Yeah,
So
welcome. I'll
participants,
take some time.
yeah, sure. Participants, thank you so much for this 60-day marathon. 2 hours every day you have given, and about 29 days we have spent together. 60 hours of learning, and lot many cover topics we have covered. Last time also we have covered QT-03 course, but with some QT-04 course, but we did it in 40 hours. But this time we have done in 60 days. You have been very patient. I am really very happy. About 500 people attending today. That's a great. Even on the last day, you are continuing your zeal and passion. Thank you so much. We have with us Dr. Satyasai Jagannath Nanda, Associate Professor in Electronics and Communication Engineering, MNIT Jaipur. He is the coordinator of Electronics and ICT Academy. We are a team of 4 or 5 people running the Electronics and ICT. Professor Vinit Saula sir is the chief investigator. Many of you have met him. Nanda sir is the coordinator, and he specializes into optimization and nature-inspired algorithms. So that's his specialization. But of course, does a lot of work in various aspects of electronics and communication engineering. So maybe we'll listen to a few of you, then we will conclude towards the end by address by uh, Nanda sir, and then vote of thanks by Vikas sir, then concluding remarks. So maybe we would like to listen from some of you. If anybody would like to share something, so you can just raise your hand. We will add you as a panelist. You can share, and then we'll listen from you, and then we can any feedback. Of course, appreciation also, and also critique. Please suggest. We want to improve. So we have Nanda sir also. We'll take the feedback to our team. We'll see how things can be improved. Yeah. Yeah. Dr. Kopaswamy, please go ahead.
Yeah, good evening to Emmanuel, sir. Is it audible?
Yes, sir. Yes, sir.
Yeah. I am Dr. Kupusamy from VIT University, Amravati. Actually, through the APSCHE, we have received this information for QT-02. Then through that, we have received this information about 03 and 4. Actually, prior to this, we did not know how to initiate the quantum computing and the quantum mechanics, some few more topics, especially with respect to this session, QT-03 and 4. You have given hands-on experience with renowned resource persons like Jay Kumar And also, Anindita madam, she has given some insights also. So it is very useful. And also, you have to continue this kind of programs for the faculty community and also research scholars community. It would be very helpful, sir. There is no negative feedback from my side because this is very useful for us in my perspective. Thank you. And also, if there is any forthcoming sessions, please share the information in the WhatsApp group, sir. Thank you.
Sure, sir. Sure. Definitely, we'll inform you, sir. Already QT-05, the brochure is shared in the group, so you can register for that course, and it will be starting on December 8th. Thank you. Thank you so much, Kupaswamy, sir. Professor Varadarajan?
Sir, namaste, sir. I'm audible?
Yes, sir.
Yeah. So, I'm Varadarajan, sir, working as a professor in Sri Venkateswara University, Tirupati. Along with me, Professor Ramashri, Bhusha, and few others are also have participated in this 60-day faculty development program. So, indeed, it's a privilege, sir, and I express my gratitude on the successful completion of this transformative 2-month development program on quantum computing and quantum algorithms. It's wonderful, sir. We have taken through meticulously designed curriculum, bridged fundamentals with the frontiers of technology, sir. But and also I would like to thank the IBM educator on quantum computing, because of which, in fact, I've already, logged into that, and it has been very useful, especially for the students. And the sessions, especially on quantum machine learning applications, that I've really cherished, sir. And of course, there are a few suggestions I would like to make on behalf of my faculty. Almost all the lecture materials, they're wonderful, but some are handwritten notes, which are very difficult to read. And hopefully, I think if these valuable contents could be made available in typed text format documents, it would be very useful. So for us to revisit the material, share it with our students and use it effectively. That I would like to make suggestion. Additionally, also I request that the contact email IDs of the resource persons, if it is available, so that we can continue to interact with them, which will we want to have an academic networking and future collaboration, sir. And of course, on behalf of the Venkateswara University and all the participants, and extend my gratitude, sir, once again to the coordinators, mentors, and support staff of the MNIT Jaipur, and of course the Council of Higher Education, Government of Andhra Pradesh, because for offering us this valuable learning opportunity, sir. So thank you once again. Thank you, sir.
Thank you, Professor Varadarajan. We'll share the contact email IDs. Actually, one of the easier way to interact with most of them is through LinkedIn. So you can send a request. Most of them will accept. So I have connected with many of them like that. So, and I have also accepted at least, I think in these last 8 months, I would have added some 2,000 people to my network. So that way, and people respond to the queries also. So you can try to look at that, right? Yeah. Thank you, sir.
Thank you, sir. Thank you.
Annapurna, ma'am.
Sir, hello, sir. Good evening, sir. Myself, Annapurna. I'm a research scholar from ITP University, sir. I'm very grateful for this session, sir. I'm attending this from QT-02 to these sessions. And in the last week, I can't able to attend due to my health issue for severe fever and all. But I'm going to revisit all the Canvas lectures again because all the sessions are very helpful for my research, sir. I didn't expect I get a lot of hands-on sessions. I'm very grateful. And moreover, Emmanuel, sir, you are always helping and answering our questions to our chat. I'm very happy for that, sir. Because wherever we are getting any trouble, we will easily approach you and easily ask any queries, sir. That is very wonderful thing for us. And MNIT organizing all the events excellently, sir, throughout the session. So I don't have any complaint. I just want to go through all the lectures and all again, sir, to revisit and rewrite at least. But I missed these 3 exams this time due to because of my health issue. I can't able to attend it, sir. That's my only thing I left with. But all the resource persons, Janani ma'am, Jaykumar sir sessions, and now Raju sir, your session, I go through every session, sir. Like every session I can able to revisit to understand all the concepts, sir. Thank you very much for all the hands-on sessions and especially collect from scratch, sir. That is what I can say, sir. We will get a lot of insights from quantum. I am very grateful for the MNIT for this, sir. For this
Thank you.
opportunity, sir.
Thank you, ma'am. We have good
Thank
news
you.
for you. We will open that quiz 3 for you. Please take the exam today. Right?
Thank you so
So
much,
don't
sir.
worry.
If it is that, then I will try, sir.
Don't worry. We will open. In fact, the permission was given because sir tried. So Saula sir and Nanda sir, the team agreed that yes, we will give the.
So, for
We
that
wanted
also
to
I
make
have.
it more strict actually, but this time at least I think QT-05 onwards things will become more strict. So this
Yes.
time we will open quiz 1, quiz 2, quiz 3
Yes, sir.
till tomorrow evening, Sunday evening.
Yes, sir.
Please complete. Okay.
Thank
So
you.
today
Thank you so
evening we'll
much,
open.
sir.
From 6 o'clock we'll open. So all the
Sir,
participants, please note. We'll put in the group also.
Sir,
Yes.
shall
Yes,
we download the materials from the canvas itself, sir?
it is better, madam. Keep a copy. We have a copy. It will be there in Canvas till March. We will keep it for these APSCHE courses. So till March it will be there. Don't worry. But better to download and keep a copy.
Sir, I hope that you will organizing this kind of sessions for scholars like us, sir, who is seeking a new
So
technology,
this
sir.
series will continue. So please don't miss the quantum computation course. Right?
Yes,
We have
sir.
very good speakers and also we'll have hands-on sessions. So
Yes,
please
sir.
join.
Thank you very much, sir.
Thank you, ma'am. Dr. Rajakumar. Next will be Senthil Kumar, sir. Dr. Rajakumar, please.
Yeah, hello. Yeah, sir, am I audible, sir?
Yes, sir.
Yeah, I'm Dr. Rajkumar, sir, Professor, CSC Department, RJM Engineering College, from Andhra Pradesh, sir. Actually, I'm following your series from QT-05 onwards, sir. Please, sir, no negative comments, sir. Actually, I'm observing from QT-05 onward, you and your team are doing amazing, sir. Even very small query also, sometimes you put 10 o'clock also the answer, sir. I also personally message you sometimes. Okay. Still, it's a very nice, sir. Nice organization. Very nice, and our government is also taking a leap to quantum computations, and it's a wonderful thing, sir. Yeah, APSCHE also, I should say, very grateful. Okay. And actually, I thought that I will miss since QT-05, I missed these fundamentals of 3 and 4 like that. Okay, but you made it possible. Okay, actually, this was my request in QT-05. And you made it true that, sir. And similarly, planning of that next QT-05, 06, and like those, sir. And my query, sir, can you please put these the answers of the quiz for QT-05 and whatever the quiz are there, okay, with some little bit explanation. So it will be helpful, sir, to know the more subject and for explaining to the our students, because our government made it like QT is almost to all universities in syllabus is there, sir. Not like a compulsory core course for all the branches like those. Okay, it will be more helpful to us, sir, if such kind of things are being made. And also, if possible, sir, please put QT 01, 02, 00 also, because they are fundamentals of quantum computation. Okay. And one more
We will
thing, sir.
conduct that course
Yeah,
shortly. I think QT-01, 0001. We'll take a feedback. How
Yeah,
many
sir.
are there, and then
Yeah, sir.
accordingly we'll try to look.
Yeah. Some of us missed that, sir. We would like to do it again one more time. And sir, those who completed QT-05 also, they can do this APSCHE QT-05. You are already
Your choice, sir. No problem. We will get 500 rupees.
Okay.
Yeah, you are welcome.
That is not a problem, sir. Actually, that I forgot to invite. Any course in quantum computation, if you see 1.5 lakh, 2 lakhs, 2.5 like those in dollars also, if you consider like, and you are giving far very good knowledge at the very very low cost. 500 also, I understood that. If something is free means everybody will follow that and they leave it. You mentioned this in Q205. I remember that. That's why we are putting very nominal fees like that. You mentioned it. That's amazing thing, sir. That is one more amazing thing that MNIT is doing. Excellent job,
Yes, sir.
sir.
Actually,
MNIT is doing.
actually,
And
the funding is from
yeah,
Ministry of
yeah,
Electronics and Information
yeah, sir. Yeah.
Technology.
Yeah,
So
yeah.
government
Yeah.
is facilitating. IBM has helped
very
in the
nice, sir.
speakers and other things.
Yeah,
Yes.
nice, sir. Because all speakers are eminent, sir. It's a long list actually. That's why I am unable to speak each and every person and saying thank you. It will over time will be over. Okay, that's it. Sir, this PG diploma or any kind of things are there. That contact program. Can you please make it, sir, during the like a Saturday, Sunday, because will be because academic side we cannot put like 10 days leave like that because students will there is a gap if gap is there. Okay.
It will not be for 10 days. It will not be for 10
Yeah.
days, but we'll
Yeah,
try
sir.
to reduce as much as possible.
Yeah,
We'll
as
try
much
to
as
make
reduce.
during
And
weekend.
centers also, sir, in AP, please see such that, sir, some centers are there. Okay.
AP, Hyderabad and Vijayawada are there, sir. When
Yeah,
we
nice,
do for
sir.
the APSCHE in summer, we'll
Yeah.
do. Then we'll go.
Okay.
We'll have more centers in AP. Definitely.
Okay, nice, sir, nice, sir. Okay. If more days are there, please like weekends like those also, we are ready to do it, sir. Okay.
Sure. We'll try
Yeah, I
to
will
do.
contact you, sir, personally, and thank you very much, sir, one more time, because other participants also I need to that. Okay. Thank you very much, sir. Thank you. Okay.
Yeah. Senthil
Yeah.
Kumar, sir, please. Yeah.
Yes, sir. So first of all, I would like to thank the you and Vikas. So both of you have done an excellent job, and the university, the AICT, academy director and the MNIT Jaipur and the Andhra Pradesh government who is collaborating with you, and jointly, even the IBM other faculties who has done a fabulous and fantastic job. And basically, I came from IT background with 25 25 years of experience, and one of the reference which I got, and this was a fabulous and fantastic sessions. And though it is more of the academic related, but where I came from the IT background, and it was a good learning experience. And it is a excellent session done by each and every faculty. I would like to thank all of them as well. That's all from my side, sir. Thank you very much.
Thank you, sir. Chandrasekhar, sir. I think with this we will conclude. We'll have Nanda sir sharing. Yeah, Chandrasekhar, sir.
Good evening, sir. Am I audible, sir?
Yes, sir.
Good evening, sir. Really, we are extremely happy for all your efforts, sir. Really, we are able to know the importance of quantum mechanics and the Schrodinger's equation, all those things after 3 decades as of now through quantum computing web series, sir. I am Chandrasekhar from YJR DMS College of Engineering, Machilipatnam, sir. Really, it is nice. And we also collected the books that you have suggested. The first book, Introduction to Classical and Quantum Computing by Wang. And
Yes.
we are able to understand the importance of the block sphere bit by bit, slowly, sir. Really, it's good. The Qiskit and all that. And you have also covered the quantum hardware processors and GPU, CPU. Very excellent, sir. Really, we are able to really feel the joy of the importance of hardware components, how they critically play a great role in doing any computation and all that, sir. Very nice, sir. Thank you so much, Deepesh Taylor ji and Vikas Kumar ji, all the team members. Thank you very much, sir.
Thank
I
you.
have
Thank
also
you.
registered for this QT-05 also, sir. We
Thank
are
you, sir.
doing. Thank you very much, sir.
Thank you.
Namaste.
Thank you, sir. Right. Namaste, sir. Thank you all participants who have also shared in the chat. I have been reading the chat also. Thank you very much for your appreciation, and also actually you are all the motivation why we are doing, because we want that our country should develop some quantum hardware. So my session today was also with reference to that only, that we should try to bring in the hardware. We have to work closer to that. So actually, let's look at making our this thing better. So let's not only learn, listen, collect the material, but let us, as sir was mentioning, I am also from Machilipatnam, sir. I studied my engineering in Machilipatnam, SVH College of Engineering. So later I did in BIT Ranchi and IIT Roorkee. So I'm very happy that we are all benefiting from this course, and many have. So with today's record, about 8,800 participants registered with MNIT for AICT courses. We have given certificates to 7,800, including all those I have counted who have cleared the quiz, 3 quizzes. QT-03. So the 7,800 people have been certified. And uniquely, if you look at, there are 3,500 people. So that's a big number. And we are very happy, because if you are not there, there is no point. And the 300, 350 odd who are there today now are the people who are attending all the sessions and are there every day. So I'm thankful to all of you. So I'll request Dr. Nanda to give some concluding remarks, and then request Vikas to share the vote of thanks.
So I congratulate first Dr. Emmanuel Pilli to take a lot of pain and effort in organizing such a mass level quantum study throughout the country. Especially his efforts are truly appreciated. Backbone of this is Professor N.P. Padhi sir, our director of the institute, who has given us the freedom to organize such courses in such a large extent. And I am also thankful to Professor Binit Saula sir, who has streamlined these programs in such a way that mass people can go through the quizzes, certification, and the process is being followed so that everybody will get the material and do all the things in a streamlined manner. Of course, there are supporting staffs whose consistent effort is there. And foremost, all these things are there because of the participants and the government's motivation towards encouraging people to learn the new technologies like quantum computing. From the central government as well as from the state government, both are pushing the recent trends in the technology towards the faculties, because if faculties will be trained, then the same knowledge will be passed on to the students. That is what the sole motivation of the MIT in this Electronics and ICT Academy project, so that all the upcoming technologies can be passed on to the faculty members. So towards that, we are organizing similar kind of many courses, and you can visit our MNIT portal and look at the upcoming recent trends along with quantum computing, other programs also like 5G, 6G communication. There are many more programs, AI, machine learning, and many applications, real life application on which the students can become employable in the next generation, especially as the technology is changing. The industry demands new type of skills, especially. And with these programs, if our faculty get trained, then they can train the students up to the new skills which is required by the industry for employment. So with that motivation, I again wish all the 350 participants, more than 350 participants, and all the participants who are absent also, in absentia also, that you have successfully completed a long 30 days, a long 2-hour section, and a very much tedious program, I can say. For long time continuously you are attending, and at the end you are getting certified. So the true knowledge, whatever you have gained in this program, will pass on to your college students so that they can get benefited. So thank you everyone. Thank you very much. And I hope you will continue your support with Pilisa again in the upcoming courses. Thank you all.
Thank you, Emmanuel sir. Thank you, everybody. Thank you. Thanks all.
Yeah, sorry for the break. Actually, Dr. Nanda had to leave for his session. There is one program he is coordinating, which is concluding today. So he is going there. So that's why we had to just take a break. Yeah, thank you so much, all the participants, for your feedback and also for the appreciation and encouragement. Yeah, please drop in any points of improvement that you would like to suggest. One of the things that we look at is that we had to add more hands-on. So we did that. And I will remember this point. Also, please be sure that we will, what do you say, we will add more implementation sessions in the quantum computation course, which will be different from the earlier QT-05. So you should be taking that. And yeah, I would like to request Dr. Vikas to share the vote of thanks to conclude. He may also add some of the remarks from his side and then conclude. Yeah.
So, good evening, one and all present here. So, finally, we all are happy that we are at the end of the session. Continuously, we were having a 1 month session, 1 month session. So, literally the way the participants and the resource person were involved in the engaging session was literally wonderful. So we hope to see that Jill in the next upcoming FTPs also. Okay. So on behalf of organizing committee, I'm privileged to basically have this valedictory session. So over the past few days, we had a very enriching sessions. Okay, and we hope you all have got benefited through the theoretical lectures, hands-on sessions, and many more discussion that has occurred over the period of time. Okay, so I hope it will, like Nanda sir said, it will propagate through your academic means whatever teaching or whatever outcomes we are expecting. Definitely, it will be reflected there. So actually I want to extend my sincere thanks to our director, MNIT Jaipur, Professor NP Padi, for his continuous encouragement for such initiatives at very huge level. Means we can say the national level. We also thank the PI of this ENICT, Professor Vineet Sahula sir, coordinator, Dr. Nanda sir, Dr. Tilly sir, we all know he is also one of the co-PI of this project. Okay. Apart from that, we also very much thankful. We are thankful for Chairman APSCHE, Dr. Professor K.M. Madhumurthy sir, Dr. Anil Kumar sir, for basically having such collaboration with us, such a big collaboration with us, and making it grand success. Okay. I would also like to thank all the resource persons for taking their time out, means out of their busy schedule. So I would personally like to thank Dr. Jayakumar Vaidyasankar sir for taking his valuable time and insightful sessions. Dr. Aswath Babu sir, Dr. A. Ananda Ramana, Dr. M.S. Dharani ma'am, Dr. Anupama Ray ma'am, Dr. Santosh Kumar Viparthi sir, Dr. Mustafizur Rahman, Dr. Ritajit Majumdar, Professor Kalol Bhattacharya sir, Dr. Anandita Banerjee ma'am, Mr. Lakshya Pridarshi, which session was, I think, given some glimpse of how industry is basically expecting our academician or our researchers to basically deliver. Okay, and what they are expecting out of our sessions or whatever learning we are having. And we had a session by Dr. Philly sir. So hope I was not there. I was in examination duty. But anyway, I hope you have enjoyed that session. And finally, the session was concluded with Mr. Raja Singh Yadav from CDAC. So with this enriching list of resource persons, we are very much privileged to have them in our FDPs. Okay, so I hope whatever learnings we had made here will be propagated through your academic deliveries. Okay, so once again, I thank you all. And for the most important thing is that I must thank all the participants actually. We all are there, everyone is there, but without the participants, definitely none of the FDPs will be successful. Okay, many of the FTPs we are witness that it is a kind of passive mode. Just one way program is going on, no one is listening likewise. Okay, so thank you so much for continuously being engaged in a discussion that made this FTPs more successful than those passive kinds of FTPs. And most importantly, the organizing committees also, like our PhD scholars and our ANICT staffs, like Nitya ma'am, the PhD scholar, Diksha Java ma'am, she is also a PhD scholar in the Department of Computer Science. And our most important person behind the scene, Mr. Dipesh sir. He was handling all the background process, all the processing, uploading, and whatever managing task was there. So that was basically done by Mr. Dipesh sir. So thank you, all the organizing committee for your support, and thank
Yeah,
you.
1 minute. I'll show them. They are just joining. एक बार इधर आ जाओ, इधर आ जाओ, पीछे आ जाओ, नित्या आप भी पीछे आ जाओ. I'm sorry. Okay. You are not hearing till now. Sorry. Let me again introduce Dr. Geeta, who is the manager of the EICT Academy, MNIT Jaipur. She coordinates the whole activities and many courses are running apart from quantum. Dipesh Taylor, who is the person who helps us in all the data management, I would say, all setting up the things and schedules, the quizzes and uploading all the material. And of course, the PhD students are also there. Diksha Java is missing today. She also is working on quantum entanglement. But Nritya is there. Nritya joined in June last year, this year, June, July, and she is going to work on quantum machine learning, not yet finalized. She's doing her coursework, but a good advantage for her, she is doing the coursework through these courses. So more benefit. So that's the team. And we have others like Ramesh Babu also helping us. And we have Manish Ji who helps us in the office related work, right? Thank you so much. A very small team, but somehow with your cooperation, we are able to work out everything. Yeah. Thank you for your time and continue these courses. We have been announcing about the PG diploma and PG certificate. For APSCHE, we will conduct during summer. Once you complete 6 courses, we will give you the list of the eligibility to do the course, and we'll arrange at multiple centers. APSCHE will coordinate. You will have to write a physical exam. So that's what will be the challenging thing. Online exams are easy, we all know, but it will be an offline and written exam, which will be more of numericals and write-up also has to be done. So maybe we'll do it like give 1 hour per day. If there are 3 or 4 days, we'll have 3 or 4 exams comprising of the entire content. So 2 courses, we'll have 1 exam, something like that we are planning, right? Thank you so much. So we will meet on December 8th. Many of you may have registered for QT-05. Please inform your friends. They can start with QT-05. Don't worry, because the basics can be picked up from the videos. Otherwise, also those who are from computer science, electronics, mathematics, and computer and physics background, they can easily understand quantum computation without the background also. So you can, it will be helpful if you do the QT-01 to 00 to 04. We have 5 courses, but of course the content is there. They can take the course because it will take a long time before QT-03, 04 will be done. QT-05 will take even more time. So QT-05 will be held in December. Please make it possible for all of you. Thank you so much for being with us, and wish you all the best. Thank you.